Oh, hello. Yeah, it's gonna be automatically recorded because it's on YouTube. So don't you worry about anything. That is, unless I get copyright striked for literally anything. But I highly doubt that'll happen today because I'll be using some Elden Ring music, but like very low in the background. Oh well, there might be one song that we might listen to just for a quick review. Yeah, it's gonna be automatically recorded. I don't even hear my music though. At least not coming through on stream. Let me. Yeah, I can't hear my own music. Amazing. Okay, don't want to drown myself out. Yeah, tomorrow's Judgment Day. It is what it is. Yeah, I've been going through some stuff myself, trying to make sure that I don't flip out during the exam. I have definitely had a history of test anxiety. For me personally, I have taken the test already like once. Okay, cool. But am I getting drowned out, or is the music too low? Stuff like that. And the music's not really that important, at least not during this. I don't think so. It'll be fine either. Well, it'll be fine if it's low. Where is... Sorry, it's been a while since I've streamed. I am trying to find my... There we go. Trying to find my camera. And it wasn't showing up for a while. Good as it is. Fantastic. Apply for accommodation. Oh no, I just, well, maybe I shouldn't be so quick to dismiss that. You might be right. I don't know. I haven't really checked the accommodations. I don't think I would qualify personally. Although that could be just an assumption on my part. I don't know. I should have looked into that. Well, again, I think at this point in the test prep process, what we're looking at is that whatever happens tomorrow happens, and then we'll live and learn. Yeah, okay. Give me a second. I think we're live. There we go. All right, now I should be on the stream. 3 times today. Yeah, I remember crying before my first MCAT. Like the week before, I was like, yeah, I'm not ready. This time is a little different. This time I still have a bit of that anxiety, but I have this thing in front of me, and that has changed a lot for me. Okay. So, just to go over what this is. Basically, I have a bit of a unusual note-taking style in that I make mind maps. And this is by far the biggest mind map I've ever made because we have 4 different sections to this MCAT, and there is just so much information. Such an absurd amount of information to know for this exam, especially considering that, like, for me, I'm a lot more into psych, and I had to learn sociology for this exam, but, you know, I am more interested in those types of fields than I am in more of your hardcore STEM fields, so Chem Phys is definitely my weakest section. But having everything on this mind map here is really helpful to just, like, keep in mind that everything on this test is supposed to be interconnected. And of course, it's a lot harder to connect certain parts of the map to others. and you'll notice that there's random like lines that jut out. I don't think you can see my mouse actually. Let me see if I can fix that. But yeah, there's just like random lines that jut out everywhere, and that is, oh weird, it's supposed to capture my cursor. Oh, there it is. What the heck? All right. I think it was not locked into the browser window, but that's fine. Yeah, I'm talking about like these lines, especially during physics. I think there's an arrangement in physics of the different fields that would make it perfect, but I didn't discover that until it was too late. And I'll have you know that I was working on this as recently as last night. So I don't think that this map is even completely it's not perfect, and it has a lot of has a couple of gaps. So we'll go over some of those gaps and how I could change this up if I were to have to take it again. But we won't really think about retakes right now as we slide into the first section. I think whatever happens, happens tomorrow, and so I'll wait for our test scores a month from now and then reevaluate some stuff. But I'm pretty damn determined to be a doctor myself, and I hope that you all are too. So I think whatever comes our way, we're all going to be strong enough to face it. So yeah, Chem Phys, my favorite section. As I just mentioned, it is not my favorite section, but we got some cheat codes here. Chem Phys is a lot of fun when it comes to the units. So first section in this mind map here is regarding units, and especially how SI units tend to play around with with interconnecting between each other. It's fantastic. So of course we got the little how do I even describe these? Just the multiplicative descriptions of each unit, being whether it's 1,000 times more than the standard version of its unit, with the exception of the SI unit of kilograms for whatever reason. I know the reason, and we'll get into that. But yeah, kilo, mega, giga, tera. I feel like the positive exponent side of units, of unit multiplication, tends to be a lot easier in this modern age, just because we have all of our like data and stuff. So the link to this map, I think it's actually might be freely available on Miro, but I wouldn't go there personally. Well, okay, if you just wanted to review for tomorrow's test, then I would understand, but I would just scrub through this video just so that you can zoom in and stuff on things that we cover. I wanted to make this freely available. I wasn't really basically, I feel like this is most useful if you can build the map yourself, essentially. So unfortunately for I think most of y'all are tomorrow test takers, so it won't be as useful to remake this entire map. But ideally, if someone were to see this a bit later, they'd be rebuilding it from the ground up, because you'll see that there's a lot of unique nickisms, that's my name by the way, in this map that are not gonna be replicable for everyone's own remembrances. But yeah, I think it technically is free because I have the like free account on Miro. I think it's you can just find it. Um, what's not ideal about that is that it might be linked to my personal account, which I don't like as much. I might find some way to change that later. But yeah, for now it's not easily accessible, at least I don't think. Sorry, don't know too much about Miro because I tend to use this for myself. Like I have a giant mind map of my own classes and stuff that are completely separate from the MCAT mind map. So I don't know. Anyway, where were we? And then the negative exponent side, dropping down from deci, centi, milli, micro, and nano, and pico. And yeah, these ones I struggle to remember, to be honest. Though remembering that micro is next to milli, and then you go even further with nano, and then pico might be a bit helpful. I don't know. For the time being, there's the other SI units here. We got meters, kilograms, seconds, amperes, Kelvin, moles, liters, and candela. Meters being distance, kilograms, well, being mass, seconds are, well, time. Amperes are going to be current. And you'll see that in total, there are 6, at least from what I could parse out, 6 very important units related to electricity. And, well, it's a bit of a mess in this particular graph here, but we'll go into it in a bit more depth later. Kelvin's temperature, moles are the amount of stuff in Avogadro, or in, well, the amount of stuff in a mole is Avogadro's number times the thing of stuff that you're looking at for. Liters is volume, and candela is luminosity. I don't think it's... I haven't really seen that in any MCAT like practice that I've done, so I don't know if that's actually really important, but I saw it in a bunch of units, like aggregation of units and why they're important in physics and stuff like that, so decided to include it. Let's see where we could start. It might be best to revisit this portion once we've covered all the different physics concepts first. So, especially because we're gonna talk about Newton's literally right now. So let's slide right into classical mechanics here. And I can't help but point out that there's a bit of a meme right now visible. I don't think, if y'all are new, which I think you are, because I kind of just advertised this on the MCAT Reddit subreddit or something, because I don't know where else to advertise this. But I am an anime related channel, and so we're gonna have some anime related memes. But don't worry, they're mostly quite intuitive, I think, or just something that you can ignore. So really, the way that this mind map should work is that I probably should have had a line up to laws of motion. I noticed that it was getting in the way of the units section though, so I kind of just threw that out. But really, I think in terms of classical mechanics, we have to start with Newton's laws of motion, in which there are 3 of them. And the first one I tend to remember being the first because it's just the simplest. If the thing is at rest, or if it's already in a state of motion, it's not really going to change unless acted by a force. And of course, intuitively, we'd be like, well, wait a minute, if I roll a ball on a plane of, like, on the street or something, it's going to stop rolling. Well, you know, it has friction, and we'll talk about friction in a second. So, there's the first one, pretty simple. Then we got the second, which is, I simplified it here down to force is equal to mass times acceleration, and I think that most people would agree that that is basically what the second law is saying. It's just discussing the interconnectedness of those well, components of physics. Man, it's hard to teach this. I always feel like there's slight knowledge gaps personally that makes me nervous about explaining things to other people, but I tried to make things as simple as possible and easy to remember for the test day, so that even if I blank out like I am right now, because I'm presenting this stuff to a bunch of people I don't know, stuff like that, the mind map should be able to tell you everything you need to know. And I do hope that the text is easily legible on stream, because I might need to zoom in a bit more if you need me to. And then the third law is every action has an equal and opposite reaction, which I used to use in my daily life, referring to like, as a kid I used to have some grudges, and I was like, oh man, Newton's third law justifies all of those angry grudges that I have towards people, because they have done an action towards me and I have an equal and opposite reaction. Now obviously that is not how physics does not translate to psychology in that same way. So don't utilize things like that or social Darwinism to mess around with matters of society. And, well, we might get into that in the psych-social session. In the meantime, this is a little reminder on the side for the third law, in that there's a cute little series of guides for various topics in physics, math, and science, called the Manga Guides to Blank. And the ones that I've read are the Manga Guide to Physics, which is most relevant here, Manga Guide to Biochemistry, and Electricity. And those are pretty nice because it has a couple of characters in each book kind of trying to understand physics concepts and kind of like having their own character arcs throughout each explanation in like physics. Megami is a tennis player, and during one of her tennis matches after a physics test, she was like, "Man, I would do so well in this match right now, but that one question during that physics exam, what is going on? Newton's third law." So it just helps me remember that Newton's third is the equal and opposite reaction, because the ball hits the tennis racket when she's thinking about that. And yeah, this anime meme might filter some people out, but basically the reason why I have this here is because Edward Elric from Fullmetal Alchemist, which is why I think of FMA, is a bit on the short side, which always reminds me of this meme, which then reminds me that FMA, which is related to Edward Elric, which is related to him being short, which is related to this meme, the Shota meme, is showing you that it is the second law, just to make sure and really hammer down the point that, yeah, this is the order of things. First, second, and third, we got it figured out, locked in. So Newton's laws of motion are related also to the rotational laws of motion, which I didn't even know about until I started looking into torque. And the first and third of the rotational laws of motion are the same as Newton's laws of motion, except they added an extra bit. Well, or like they replaced the word of motion with rotation. Oh my God. The most notable part, though, is that the second law of motion, rotational laws of motion, refers to torque specifically. And now torque is going to be, and for the programmers out there, I know that this is not the correct notation for what I'm about to say right now, is that acceleration is proportional to net torque. And this is something that's really important to me about torque, because I was like, why is torque important? Like, I conceptually understand that it is related to why we push a door on the furthest end as opposed to the closest end. But like, what does that actually mean physically? And what that means is that when you push a door on the furthest end, that increases the acceleration. And so you can push that door a lot faster with less force, essentially. And then it's also inversely proportional to the moment of inertia, which is intuitive just because inertia is just the resistance to change in velocity. And we've got that right here, interconnected with mass, which is a fundamental part of classical mechanics. And for torque, going back to torque real quick, this is that equation that will describe torque for you. Of course, theta tends to be 90 degrees. Again, physics is not my strongest subject. Not really sure when we would see theta not be 90 degrees in most questions related to the MCAT. And of course, this is one of my favorite memes regarding rotation. So I don't really know if sine theta is going to be particularly relevant, but just remember that torque tends to be, well, opposing the direction of rotation. I don't think this is necessarily describing torque in an intuitive way. Because torque tends to be more like, let me grab some examples here. Where is it? Torque about a point. Distance. Yeah, I think the opposing part is more so that that it's opposing inertia, and I think I just wrote that, because torque is just the describing the force that is related to length. It's like the cross product of that, and so it wouldn't oppose the direction of rotation. It would just be the rotation. So I believe that this is actually direction of rotation, of inertial rotation, I think. And of course, I would greatly appreciate any corrections that you guys might have in the chat below, or to the side, I mean, because again, not my finest subject. And we'll get to my favorite subject once we go through all of this. So, all right. So torque was a bit of a detour for us, because really we should start, when talking about classical mechanics, with the most simplest concepts, displacement, and then we'll talk about mass in a bit. So displacement, well, you know, it's distance, but in a very specific direction. And when we divide that displacement by time, when we find the change in distance over time, we find velocity. And then velocity changing over time is related to acceleration, or is acceleration. And we already mentioned mass here, and that is related to momentum, which is kind of like it's oh my god, I could have explained this easier a while back. I'm just gonna personally remember the equation, because momentum, for whatever reason, tends to not be the most intuitive to explain unless you consider impulse along with momentum, because impulse is actually just the change in momentum. And I don't think I've ever seen anything related to impulse in the MCAT. It was just a thing that I found a little bit helpful, because when the tennis racket impacts the tennis ball, in that manga guide that I was mentioning earlier, it is changing the momentum by hitting the ball with a force for a certain amount of time. And so the momentum is just kind of like that. It's kind of like the... I have to choose my words carefully. I don't want to say it's like the power of the ball, but it's like the... Let's see if I can find a good quantity of the motion measured by its product and mass and velocity. Magnitude... I mean, these are fine. I just remember that there was like a really good explanation for it that I'm surprised I didn't note down, because there was a really nice simple version of that, defined as mass in motion. That could be a pretty simple one to remember. Momentum being mass that is in motion, I guess, but that doesn't really explain why it's important to remember, or why it's important. I don't know. I'm just not gonna think too hard about it, because it's gonna bother me a little bit. And the whole point is that we're chilling today. Today is a chill day. So, gotta internalize that I might have a slight gap, and then I'll put it to the side. Put it to the side. So, I do want to shout out vectors, because velocity and displacement are specifically words that have a direction. And when we talk about vectors and how to add them together, there's just a thing called the tip-to-tail method of vector addition that will allow us to very simply put the vectors together to find their additional kind of magnitude and direction. And now we can hop back in with acceleration, because acceleration has a very unique cousin. Well, not really cousin. There is a very unique type of acceleration that is acceleration due to gravity, and that is simplified to 10 times, or 10 meters per second squared. Although, if you've ever been in a physics class, you would probably have used the 9.8 version of that. But I think, since we're not going to be using calculators on the MCAT, I think it's probably easier just to remember it's 10. And 10 is a number I like a lot. So yeah, that's just an easy way, or that's just a simple version of that. And that is, of course, related to gravity. And of course, there's a universal gravitation law, which describes the interaction of two objects, because everything in the universe has a force of gravitation towards it. And the way I remember that is that no matter how ugly you are, everything in the world is attracted to you with a force inversely proportional to its distance squared. And that's just from a meme video that I really, really liked. And you'll notice that there's a few mnemonics that are throughout this map that will be a bit crude. And things that I won't agree with. I don't agree with ever calling yourself ugly, because I just don't believe in that being a thing. But again, I'm a psych student. We'll talk about self-reflection in a bit. God, I'm hyping that up so much. We still have the rest of physics to go through, and BB, but that's fine. And there's a universal gravitation constant. I'm gonna be honest, I don't think I would even remember this during the exam. I'm just gonna like hyper-focus on it for a second right now. 6.6 times 10 to the negative 11. And I'll try to remember that. But as this bit of a meme has described, there's that gravitational constant interacting with, multiplying with the masses of the two objects, and that force between them will be described by that distance between them squared, or divided by the distance between them squared. Yeah, so weight is going to be your mass times your gravitational acceleration. And we can intuitively understand this because weight is referring to the force that is being applied by gravity onto us. And of course, we know that that is going to be mass times acceleration, except this is a unique acceleration called gravity. And that is related to potential energy. Energy is a fun concept because potential energy is going to be describing what an object can potentially show us in terms of kinetic energy. Due to, in this case, gravity, this is the equation for describing potential energy through gravity. And so when you have an object on a very high platform, it has a lot of potential energy that is going to be turned into kinetic energy when it is dropped from the platform. And let's see. I feel like explaining energy is a lot more intuitive once we get into why or how it's related to a bunch of different stuff, because energy is really cool because it is constant, and because it's constant, it is actually just changing between different forms of energy. Shout out to elastic potential energy. Again, there's a lot of stuff in here that might not even show up on the exam. But, you know, elastic potential energy is a bit easier to remember just because it looks like the kinetic energy equation, which you'll find down here. Half times something times something squared. And in elastic potential energy's case, it is half times the spring constant times the natural length, or sorry, distance beyond natural length squared. So that distance from that natural length is what is causing that potential energy to exist, because the spring is like, yo, I wanna go back to normal, but I'm getting stretched out or squeezed right now, and I wanna go back to normal. So that is why that is showing up on my potential energy equation. And spring constant is related to the material of the spring. So joules are the unit of energy that we tend to think about first. But of course, you always have to remember that it is also related to calories. And I think that this is actually kilocalories. Yep, that is actually kilocalories. And the reason why that could be confusing is because the way that we label kilocalories in just general society is by giving it a giant uppercase C for some reason, as opposed to the lowercase calorie, which is just the smaller one. And calories will show up over there once we get to thermodynamics. Oh my god. Again, there's a lot of information, and the thing I like about the map is that I can zoom out anytime and just be like, okay, we just covered this entire, well, most of this section, and that's, you know, it's a good part of it. It simplifies it down. Especially when you consider that really, in this physics section, I've got, what, like, basically 1, 2, I'm going to include waves along with electromagnetism here, 3, 4, and we're not going to include thermo because it's all the way up there, it's all on its lonesome. So really there's 4 islands, 4 big islands related to physics that we've got in the bottom right corner of my map. And so that makes things a little bit easier on the heart to be like, okay, while there's a lot of information, they all congregate into these giant chunks that if I remember some of the parts in that chunk, then hopefully I can just have that thing that I'm searching for in my head show up when I'm taking this exam. Okay. So we looped around to energy. I think we might want to... The thing is with this mind map is that because everything is interconnected, we don't really have like a simple pathway to follow. So I'm sorry if I'm kind of like confusing you guys a little bit, but I'm pretty sure that that if you just like lean back a bit, you'll see that this is just kind of a web of interconnectedness, and we're just hopping between different points in the web just to illustrate certain points better than others. And also I apologize if my explanations for things are confusing you, because my mind works in such a way that I describe things in a way that might be a little different from how you studied it, but just keep in mind, you know, you studied one way, I studied one way, and this thing that is in front of us is just an expression of my kind of like feelings, I guess, towards the material. That is unique to me, but you might be able to glean a bit more intuition from another person's style of study. So that's what the hope is for showing you this. And of course, I think that for my folks that are showing up for a later exam, you know, you make your own mind map, and hopefully this is inspiring some people to do that. So let's go back to second law. It's going to describe force, and we're going to we're going to use force to describe something very cool called work. And work is just the force times the distance, displacement. And we know that work is a process function, which means that we care about its pathway in life, as opposed to a state function, which is when we don't care about your pathway in life. You just show up. They just turn up. Process function, you know, we care. We care a little bit. So the reason why work is important is because it is kind of like describing the change in energy, right? So the way that I like to remember that is that when we want to change the potential energy of a thing, we're going to lift it up, right? So we're going to lift up an object, lift up this pen, for example. And when I lift up this pen, I'm doing work on the pen that is proportional to the distance that I am moving the pen from its starting point to its new point that has a new form of potential energy, or new potential energy. And that change in potential energy is going to be described as the negative potential energy, which, I'm gonna be honest, isn't the most intuitive thing in the world, but you know, you just remember that work is essentially basically, oh, I should have just explained this earlier, because energy has a lot of different things that it's related to. The other thing that's amazing about energy is that the ability to do work is described by energy, and that basically means that the amount of work that something can do is stored within the energy, stored within that joule. So yeah, that change in energy, that ability to change energy, is all conservative. It's all conserved. It's everything in energy is going to stay the same. Yeah, that's the simplest way to put it. And we're just shouting out conservative forces here because that is related to this equation for reasons that I'm trying to remember. Can't do it. Can't remember it right now. But that's fine. Yeah. It's the day before. I'm not going to worry about it. Not even going to search it up tomorrow, or not even going to search it up after stream. So whatever. classical mechanics is almost done. And that means we get to look at a really cool thing called the free body diagram. And this is a free body diagram of frictional force specifically, because it's the one that I tend to kind of like struggle with a little bit. Just imagine that this dynamic equilibrium block is on a slope, and here's the incline of that slope. It has an angle, and that angle is going to be the same angle between the perpendicular factor or aspect of weight to that slope and the weight that is, well, there we go. Yeah, this is the line that is actually the weight in parallel, while this is just simply weight. So it's really the angle between the perpendicular weight and weight itself. That is the same as this angle of the incline. And of course, shout out to normal force, which just recently found out that this is basically the collision force between two objects, so that an object doesn't pass through another object. If you're familiar with game design, there is kind of like a thing called collision in games, where you're trying to make sure that things don't pass between each other, or if you want to like detect something impacting another thing. And so that interaction is actually normal force, which is going to be equal to that perpendicular weight to the incline. Frictional force is going to oppose the force of weight, the force called weight, that is parallel to the incline, and that is best remembered by its equivalence to, well, actually, yeah, this equation is literally just saying that frictional force is the same as weight parallel to the incline, and that can be multiplied by theta if you have if you have it there. And just imagine all that stuff interacting with one another. I'm getting tired of classical mechanics. We did a good job, though. We've already gotten this covered, and we've unlocked newtons and joules, force and energy, to this weird, like, electrical circuit that we've got going on over here. And you can see that the blue lines are actually just explaining that this is a thing that is being multiplied, and the reds are things that are being divided. And we'll revisit this, especially for electricity, which we'll get into right now. So electromagnetism. Oh, yay. Well, the absolute basics go down to voltage, current, and resistance. And voltage is going to be best remembered by the difference in potential energies between the two ends of the thing that has voltage, or the thing that is describing voltage, being a battery typically. And that is best explained by voltage is being equal to current times resistance. And current is best remembered by the fact that it is the charge over time at a certain point, typically on the circuit itself. So at this point in the circuit, we've got some charges passing through at a certain point in time, or at a certain time frame per time. And that can be described by amperes, which is coulombs, which is kind of like the standard charge unit over time. And we know that current tends to be the same, or wait, current, let's see if I can describe this properly. When current is split between two lines, those two lines will be added up to, the sum of those two lines will be equivalent to the overall current that was described before the junction occurred. And so that's the junction rule. And then the loop rule is just basically like the current will eventually equal itself once it reaches the point of voltage, or the voltage thing. Okay. Maybe not the best idea to have to explain everything with my voice before the test. I don't think it's gonna be that bad though. I think it will be okay. For now, there's resistance, and that was already related to VIR, which is Ohm's law. And resistance has a property that is described by resistivity times the length of the wire divided by the cross-sectional area. And resistivity is also related kind of to the electrical conductivity of different things. So non-metals have a higher resistivity, while metals have the low one, which is intuitive to how we understand the technology that you and I use. It's all in metal, so there you go. Resistors are going to be related to capacitors, which are basically like plates that have a voltage difference. So they're kind of like batteries, but they're batteries that get loaded up during the circuit being in action, basically. And there's some random thing here called the cutoff frequency. I wouldn't worry about this too much. It's just a thing that I saw on a test one time, and I was like, okay, I'll put that in there. I don't think I'll even bother to remember it myself, but if you want to, you can. Just remember that resistors and capacitors are weirdly inversely related when it comes to their properties in series and in parallel. And in series, I think the easiest one to remember is that in series resistors are going to be additive, and then you can just figure out the rest immediately from that, because you're like, oh, this one's the parallel one. It's 1 over R equal to 1 over R, 1 over R. And I know that capacitors are going to be opposing this, so this is what in parallel capacitance looks like. They're additive in that case. And then, yeah, in series capacitors are going to be like that. And capacitors have the unit farad. And if we look at the unit farad, we notice that capacitance can be best described by the charge per voltage. It can also be described by the time being divided by ohms, which ohms are the... Why am I blanking on ohms? Ohms is not resistivity. Or wait, no. Ohms is... no. Ohm times meters is resistivity. Ohms is just resistance. Right? Yeah. I was like, wait a minute. Wait a minute. And that can be easily determined by the fact that it is equal to voltage divided by amperes, which if we were to just reassemble that, we can just get Ohm's law easily by multiplying amperes by ohms, and then we're like, oh, that's equal to the voltage, equal to volts. Easy. All right. Whew, okay, freaked me out for a second there. And for some reason, coulombs, it's not considered an SI unit, it's just, you describe coulombs as amperes times seconds, but the most intuitive form of coulombs for me is that coulombs is kind of the base value because it's the charge, and the charge is what really matters at the end of things. And so amperes, I would say, is the thing that is actually getting described by being coulombs per second. Oh boy, we have some other stuff to get through, including watts. Okay. So electrical potential difference is what voltage is, and we've got electrical charge over here, and electrical and Coulomb's constant, which is we'll get into that in a second, divided by the distance. Yeah. Oh my god. So these are an assortment of different equations here that are best remembered by the mnemonic "fuck you, evil vampire," which is just fantastic. And really, you can start by remembering Coulomb's law, which is an awful lot like universal gravitation. Looks a lot like Coulomb's law. Interesting. If you think about it like gravitation, or as with gravity, every object has a force of gravity. Every object, at least when it comes to talking about Coulomb's law, is probably going to have its own charge. And so we see that there's the charge of one times the charge of the other. And of course, gravitation has its own constant, but we have the Coulomb's constant for describing electricity stuff. So that is replacing G, and R is the same. It's the distance between those two electrically charged objects. Okay, so fuck you, evil vampire is fantastic because we can just be like, well, then I'd multiply F to the U, and U is electrical potential energy, and that is just multiplied by R. Hopefully you just know that. But for me, it's like, if we multiply by R to the gravity, it's going to be... Nope, not going to think about it too hard right now. That's why I would love to work on this map a bit more, but I'm going to choose not to. We're going to divide by Q to get... we're going to divide by Q to drop down to evil vampire. And the force of the electrical field is not going to be including a second Q, because it's like, I only have one charge to think about when I have made an electrical field, so I don't really know why you would include that. So there you go. You only have one charge to consider, whereas potential difference, also not going to think about the charge difference that was present in potential energy with I guess two charges. we're going to just stick with 1, and we'll just have the most simplest of the FU Evil Vampire quadruple. So we talked about charge a lot, and charge is simplified down to the charge of an electron and how many electrons there are, and the charge of an electron is that. And that is what a coulomb is. In proton charges, for some reason. Yeah. Electrical charge is that many coulombs. And hopefully I can remember that. 1.6 times 10 to the negative 10. All right. Coulomb's constant drops down to being described like this. I personally haven't seen, haven't been tested on that particularly, but, you know, it's there. And that E0 is not to be confused with electron charge. It's just the vacuum permittivity, which could be related to that. I don't really know. But that is also related to the magnetic constant. And suddenly, we're at the speed of light. So this entire thing, this kind of like little step by step stairway to heaven, to Coulomb's law, is actually just so that we can get back down to speed of light. And light, as we all know, is a electromagnetic wave. And it's a quite funny one because it's like they're waves of magnetic and electric fields that are offset by 90 degrees. So they're like that. And that's just really funny. And we can remember that speed of light is equivalent to the wavelength times the frequency. Wavelength being, if we go all the way up to waves, distance between the same points in a unit of that wave, in a same distance between, you know, the crests of the wave or the troughs of the wave. It's, you know, it's the same, it's the singular unit of the wave that is being repeated over and over again. That distance between those 2 points that describe that unit of that wave is the wavelength, which also happens to be the period if you are considering time to be a related factor. And there's some other descriptions here, including amplitude, which is kind of like magnitude, the size of that hill between the crest and the trough. But there's also nodes and antinodes, which are related to standing waves, which we'll get to in a second. For now, we're talking about light a bit more, with the energy of light being, well, being described by this, which includes Planck's constant, times frequency, or, you know, we just discussed that frequency is in this equation. You can just plug it in here. And then you're set. Then we have energy of a photon, which is just that the speed of the photon replacing the frequency, which is cool. Energy also can be described like this. When we're asked about the photoelectric effect, which is just basically the amount of work we need to put in to launch a electron out of a thing and out of an atom, we have basically described we have basically described an energy equation. And that looks exactly like kinetic energy plus work, you know? All right. So, where was I? What is going on? Honestly, it's... I am struggling a little bit to describe things because, like, this is not my realm of expertise. But if you are just wondering what is going on in general, we are currently working through this giant map of MCAT stuff. And I'm starting with physics, which is not my strongest suit, but we're already done with one branch of physics. We're down to electricity, and I'm just finishing up light. And I'm gonna also describe some electric field stuff, and then we'll switch into waves in a second. So that is what is going on. Yeah. Let's see. Almost done with light. Here are the different wave forms that permeate throughout our world. The longest wavelength is at the end here with the radio wave, and the shortest wavelength, which also has the highest frequency, because wavelength and frequency are, to be a bit reductive, inversely proportional for the most part. And so we see that visible light is set right here in terms of the wavelength at 750 nanometers to 400 nanometers. And for whatever reason, sometimes some questions ask for you to know that. So there's that. Magnetic field is going to be describing a bunch of different things because it's related to forces caused by it and currents caused by it, or that are created, that create it. So first of all, let's talk about a moving charge. Moving charge is described by, or moving charge has a force that is the cross product of velocity and the magnetic field, and that is multiplied by the charge just to describe the magnitude of that force. And Lorentz has a handy-dandy right-hand rule, which is going to be on your right hand, pointing. Yeah, so right hand, there we go. So we got the thumb typically describing force, which is the same as Fleming's, which we'll get to. Velocity is the pointer, and middle is magnetic field. Fleming's is describing when we have a current, how that forms the a current in a magnetic field, how that forms the force. And since the force is the thumb for both Lorentz and right-hand rule, we can just have, if we were to point the magnetic fields like this towards the camera for me, except my hands are flipped on your guys' end, or maybe not. I'm pointing my middle forward, and I'm pointing my pointer forward on my left hand, on my left hand, and that is pointing towards the magnetic field, and that has the same direction of force as well. So you would just have to remember that I'm flipping off the camera. That the thing that's unique to left hand and right hand are going to be the current on the left hand and the velocity on the right. Right. Ampere's right-hand rule is the fun one because it's very simple. You just have the thumb being the current, and then magnetic field loops around that current really nicely, kind of like wrapping, I was about to say wrapping a hot dog with a hot dog bun, but I don't think that's the best way to explain that. Or maybe wrapping a burrito. But the burrito would have to be a thing that has like, it doesn't really matter. I feel like amperes is pretty straightforward if you just want to remember that it's just looping around with your right hand. That's it. Okay, so we're finally done with electromagnetism for the most part. I think there's some extra things that we could have talked about, but that is not what I have included in my map, so we'll just hop back down to waves, which is connected to electromagnetic waves. So we'll just ride the waves over to waves. And we've already kind of talked about, or we've already mentioned antinodes and nodes, so let's talk about standing waves. All right, so nodes and antinodes, kind of annoying to remember for me. But the way I remember it is that nodes are going to be the ones that aren't moving too much. They're just literally supposed to stay the same when the standing wave is in action. So they'll be steadfast and hold their ground, and that's what makes them nodes. But antinodes are kind of the rebellious ones. They're like, okay, you know what? Joke's on you, node. I get to jump between the different crests and be like, wow, look at me. I'm a crest and a trough. Ooh. Wow, antinode, so rebellious. So, ooh, okay. So standing waves have some properties to them. And we're going to be thinking about harmonics and resonance. Standing waves have a harmonic that, okay. So wave speed is throwing me off for a second there, because it is more so just related to frequency. Okay, basically wave speed is here because it's actually related to this thing, but I wanted to put it in waves. So, whoa, okay. So that's why it's here. But don't get too distracted, because it's just because I was trying to have things close together that are semi-related. Wave speed is related to frequency, which is here. Fundamental frequency is here. Oh my god, Elden Ring is going ham, which is to be expected. Okay. Oh, right. Okay. That's why. Whoopsie daisy. Okay. That's why it's here. Wave speed is going to be describing fundamental frequency, which is just the frequency that is fundamental. It's the first one. So when we have a standing wave, there's different harmonics that are described by that wave, with the first harmonic being the most simple version of that, because, and we're going to talk about resonance too, which is related to harmonics, because when we have a tube that has a closed and open end, we have different harmonics related to that, and a closed end, the first harmonic for a closed end tube is going to be the first harmonic, the first harmonic for a closed end tube is going to be the simplest one, which is basically you have one antinode and then one node, and it's just like a slight slope between those two. And whoops. Okay, I'm jumping around a bit because hold up. Okay, sorry. When we have one open and one closed end, I'm actually describing this thing here. But basically, when we have a closed end on a tube, that is the node. And when we have an open end, that will have to be an antinode. So given that those rules are in place, we know that the first harmonic for an open-ended tube with the other end closed is going to be a singular antinode and a singular node. Whereas in open end, we know that there are going to be two antinodes. So the simplest harmonic between those two would just be like one antinode on the opposite end. Like if you were to imagine the tube, it would be on the bottom of the tube and the other end is going to be on the top. And fundamentally, we look at this frequency. Give me 1 second. The problem with this map is that it's an aggregate of a bunch of different stuff, so if I didn't connect the dots correctly, we are in for a bit of a mix of a messy time. The important part regarding open and closed ends is going to be the wavelength being described by the length of the tube. Divided by the specific harmonic that we're talking about. So the whole point of why I was mentioning the different harmonics is because that is what that n is. N is the harmonic number. Let me get a drink of water. And so with one open end, we have the wavelength described by multiplying that length by 4. And I could show you what that looks like, but I'm not going to right now. You can just imagine if you have one antinode and another antinode, you'd have to multiply that by 4, there we go, to get the wavelength. Sorry, if you have one antinode and one node, that's why I was getting confused. Sorry. It's going to stop in the middle, and so you'd have to multiply that by 4 to get the full wavelength. There we go. Whereas the open ends, you'd have one antinode here, one antinode there, and then go up, and then go down again. And then when you go down, that is already the second half that wavelength. And so that's why you would just multiply that by 2. Assuming that we're just talking about the first harmonic. If you have second harmonic and stuff like that, you'll divide by 2, or divide by whatever harmonic number that is. Okay. And this wave speed stuff is why we have this here. This is just basically plugging in frequency. Sorry, plugging in wavelength into the frequency function. There we go. And so that's why you get this. Also, if you're asked about the tension of the cord, Apparently, the more tension there is, the higher velocity of the wave. That's just kind of intuitive if you have played around with instruments before. If not, then just like remember that. So waves also have a bit of interference between them. Destructive ones are going to be talked about in the single slit diffraction situation, and that is shown by the angle, the sine of the angle between each, not antinode, but like the point that they have destroyed each other, essentially, the point at which they have resonated and destroyed each other between the different waves. That point is where is n along that kind of like line of dotted diffraction, and that dot, the angle from that dot to the slit is theta, and the width of the slit is going to be interacting with the wavelength of the wave. Just remember sino na for single slit. All right. I'm like trying to describe abstract concepts, but like it's hard to describe without showing you the thing. You have the single slit, and then there's all the lines that go off of that single slit, and that diffracts on the thing, on the other end. Waves are also, well, sound is waves reverberating through the air, and for whatever reason, we care about the Doppler effect, which is actually kind of cool. Because basically, if you're approaching an object, or an object is approaching you, and it is emitting sound, when you approach the object, the sound waves seem like they're kind of like compressing, because you're like, you're basically traveling along these waves a lot faster. Like you're on a speedboat along a bunch of waves. So the waves should be the same from the perspective of the object, but from your perspective, you're moving a lot closer to the thing, and the waves seem like they're going faster and faster. So it sounds like something is a lot higher frequency when you're approaching it, and then when you're leaving it, suddenly those waves kind of like get a lot easier to travel along, and so it feels like the frequency is expanding, and or the waves are expanding, and so the frequency is getting lower, yes. So, fun thing about sound, we measure those in decibels, and decibels are kind of a log function of the intensity. I1 and I2. Okay, the way that I'm going to remember this is just like, when you add decibels, you're actually multiplying. And for whatever reason, in each 10, it's going to be times 2 perceived loudness. When it comes to intensity, that is actually connected to power, which is connected to energy. Energy drops down to here. And power is describing the energy that is being done over time or sorry, the work that is being done over time, which happens to be labeled with the joule. So it's work done over time, or energy over time, and intensity is how much of that power is being distributed across an area. So watts are what we're going to be interested in when it comes to power, energy over time. Okay. Okay, that's waves. That's electromagnetic waves. That's electromagnetism. And we're in optics now. And remember, that is basically half of the chunks when it comes to the physics section. So we got optics. Okay. Where to start with optics? We can start with index of refraction. So, since we just talked about speed of light and light itself, we noticed that index of refraction of different materials is going to be that speed of light compared to its actual velocity. So speed of light is divided by the velocity of light in a medium. And that relationship is what describes the index of refraction. The thing is, you have to remember that the angle of incidence that we care about is the angle between the light ray and the normal along the glass plane or whatever material that we're reflecting into or refracting into. So angle of incidence between this perpendicular thing and the light ray. That's the thing that we care about. And here we go. We've got angle of refraction here. Again, between this perpendicular and the light ray that is actually being shown. So there's our light ray going along, and our angle of refraction is going to be here. And again here, because that is the perpendicular normal to the material that we're passing through. And this is best described by Snell's law, which is right here and here, which is just relating the different index of refractions with one another, with the initial angle of incidence being represented here, and the angle of refraction that is resulting from that initial angle of incidence in the second half of the equation because of the new index of refraction that we're going through. So now we got the power of the lens and its strength, which are both going to be 1 over the focal length. And the focal length is the distance between our lens and the focal point, which is basically where the light rays merge from the lens. So when the light rays hit a convex or converging lens, that would be the one that's curved on both sides, we're going to see that that focal point that is created is going to be a real image because it's real and it's not in some virtual plane of existence, whereas a diverging lens has a virtual image because the light rays kind of like hit it from the different sides and then refract in a way that's going out. And when it goes out like that, there is a point where those lines would theoretically intersect that we see as a virtual focal point. And diverging or concave lenses are what treats myopia. That's why I wear these glasses. And myopia basically is, without my glasses, the focal point of the lens in my eye is actually not hitting the retina. The focal point is like before the retina. If you imagine that the retina, let's say that focal length is like the retina. Focal point would typically be here for a normal like 20/20 vision or whatever, for something that you're focusing on. However, for me, the focal point is over here for some reason, and that makes it really hard to see stuff in the... well, we'll talk about distance in a bit. If the object is at a certain distance. Here's some eye anatomy, just to quickly review. Well, for the light passing through, we've got the cornea, iris, pupil, lens, vitreous humor, which hits the retina, and then that goes... the way that I have this labeled is because it hits the retina, and the fovea is the highest concentration of those cones and rods. But all of that information goes into the blind spot, which is actually the optic nerve connection. And conjunctiva is like the stuff around the eye, and the anterior eye chamber is kind of like in between the cornea and the lens. And then we have this other stuff which I don't think you really care about. The sclera is just like the white parts. I don't think you need to know too much about that, so we're good. For the time being, we've got spherical mirrors, which are kind of like the cousins of concave lenses, because they also have diverging light rays, and so they would also create a virtual image. And the radius of the curvature tends to be 2 times the focal length. Okay, so the actual stuff that I've seen on practice exams is trying to relate focal length with the distance from the object and distance from the image. And if we connect the lens strength with this other equation describing lens strength, we get 1 over focal length is equal to 1 over the distance from the object plus the distance from the image. And you can just be like 1 over phi, 1 over phi, 1 over FOI. So there we go, that's optics. Oh, right, okay. So I forgot to mention back in sound waves that we can describe the velocity of sound through fluids by square rooting its bulk modulus with the density. This is what P is going to be, and we'll hop into fluids in a second. Bulk modulus is the compressibility of a fluid. I mean, yeah, it's just, you imagine sound wave going through fluid, you're like, how's that compressing the fluid such that I can hear it through the fluid? That's how bulk modulus is determining that. B is equal to the change in the pressure over the change of the velocity of the wave proportional to the velocity. Change in the velocity over the velocity. Yeah. Or sorry. Velocity. Volume. Change in the volume. Divided by volume. I don't have an intuitive explanation for that. It is just something that I would remember, but I don't think you really... This is some low yield stuff. Bulk modulus. But it exists. So we could shout it out. So hopping into fluid mechanics, we could talk about a bunch of different stuff. We've got gases, we've got buoyant force, and we've got flow. We can start out with gases. Gases has my favorite equation of all time, PivNert, which is just, it just sounds so funny. PivNert. It's great. Just took the MCAT today. How was it? How was it, Haley? If you don't want to talk about it, that's fine too. We're vibing. I just hope that it went well for you, and if it did not, then you're just gonna vibe with it and see what happens when you get the test score back, because we all have different ideas of what we'll do when we get that test score back. Chem Phys is brutal, yay! All right, voiding is definitely an option. For me, yeah, it depends on how you really feel about it. I would typically say that you would want to not void too often, just because it's like, I'm pretty sure adcoms can see if you void an exam, but it's like, not only that, you just don't get the feedback of the score, but you know, it is what it is. Yeah, if you felt like that test was not it for you, then yeah, it makes sense. Things went well. Cars was easy. So I'll just mention that I do love cars. Cars is my favorite section, actually. So I would hope that cars is hard so that so that you can see a bit more of distinction. Yeah, they can't see it. Fair enough. So whenever you feel like retaking it, you'll know, you'll know how that test feels like. I've taken it once before. I didn't void it for that. Felt like my action and my final score was, you know, it was a nice score. I liked it, but it wasn't the score that I wanted, and so I'm trying to make sure I get the score that I want in this case. However, as y'all can see, physics is kind of a rough spot for me, so hopefully the chem phys isn't too shoddy, but the rest of the test I'm hoping has improved by significantly. Target is 510. Nice. Yeah, it's crazy how this test is scored. Because when you mention 510, it's like, that's like 80th percentile almost, or something. I don't remember the exact number for it, but that's like 80th percentile. And then the one that I would love to have is 515, and that's 90th. And it's just like, so I have to beat a bunch of really smart people? A 90% of them? And it's just, that's a little silly, you know? It's a little silly that we have to compare ourselves so heavily against each other like that. Of course, the people that are scoring on the same day are actually not competing against each other. They're competing against basically like a Mario Kart ghost. But 90% of that Mario Kart ghost, you have to score above. It's like, wow, goddamn. Yeah, exactly. Man. Yeah, it's just, it's helping me a bit to remember that the percentiles are a bit absurd, to like ease the nerves of the test, because it's like, man, That's so ridiculous. That's so silly. I wish it didn't have to be like this. And I think that um, there are ways that once some of us go into our professions, that we can change some things from the inside, but who knows? That's a bit of a far-reaching goal, though. And for now, I'm just hoping that I can actually like be a physician and help people out the way that I envision, which is one-on-one with patients, and then hopefully figure out some ways to help out the next generation. If I can actually be a doctor, you know, it is what it is. We'll see. We'll see how things pan out. I'm sure that I personally have some backup plans, and I'm sure that you guys have some too. But you know, for now, I'm thinking I gotta do it. I gotta be a doctor. Let's do this thing. Not a good diagnostic, especially when there's no anatomy. So I have seen some anatomy on the test, on some practice tests, which is why I have a section for nephrology, all the way over here. I have a small anatomy section, and I just went over eye anatomy. For some reason, it does show up, but it's not like, it's not at all in depth. It's just kind of like a random, like, hey, do you happen to know how a nephron works? And it's just like, okay, I guess I do, but that's not what is reflected in the rest of the test, so I don't know why you're asking me that now, but okay. But yeah. Test is whack. I wish I could kind of like be in those conversations when they're designing the test and be like, hey, wait a minute. I feel like we should be testing this part, this thing instead. But we've got what we've got for now, so we'll just vibe with it. Okay. Hopping back into gases. Pivner. I got totally tripped up in a practice exam because they were asking me if N was in moles, which should be the easiest thing to answer in the world, but for some reason I froze up and I was like, moles, do I multiply Avogadros? Do I divide it? Yeah, N is in moles, so if you're asked how many things are in the gas, you're like, I multiply by Avogadro's numbers, because that's the amount of stuff in a mole. Oh, the kidney. Oh, you're talking about anatomy, like, as in... I always get a little confused when it comes to the distinction between anatomy and physiology, because I always think about them together. Do you just mean, like, just the sheer knowledge of, like, where everything is? In which case, yeah, I understand what you mean. Because, yeah, you don't get anything related to, like, memorizing which muscles are where and stuff like that. So, if that's what you mean by anatomy, then yeah, you don't get tested on that. I'm just surprised by random physiology, because it's like, the rest of the test doesn't look like that physiology stuff. It's more biochemistry, which is more molecular in nature. So I always get a little bit surprised when I see nephrology, because I was like, what? Looks different, but it is what it is. Right. So there's a bit of work that you can do with gases that expands and compresses them, and that is inversely related to the pressure and the change in volume. WPAV. I'll try to remember. And when we talk about gases, we got to talk about standard temperature and pressure, STP, which has a bunch of values. I haven't figured out a mnemonic for this. for me, it's rote memorization for now. Even then, I don't know if I'll... Well, we'll see, we'll see. We'll see what I remember on the test, but, you know. Ideally, I would have more mnemonics. That would be cool, but for now, that's what we're working with. And of course, we're talking about pressure. I want to shout out hydrostatic pressure, but let's... Yeah, no, we can shout it out first. Hydrostatic pressure is density times gravity times h, the height. And you just imagine that being the pressure bearing down on a point in space. Yeah, thanks. Thanks for the good luck. And that's the other thing that's crazy about this test. There's so much like luck involved too, because you just we might not even be tested on buoyancy. And it's just like, why would I even cover this? Why did I study so hard about buoyancy when it doesn't even show up? And instead I get I have to like describe what voltage means. Like, oh man, it is what it is. Yep, hydrostatic pressure bearing down on a point in a liquid or in a fluid. And you get barometer height by equaling the hydrostatic pressure from the outside of the barometer with the pressure inside, I think. I am pretty sure that's how that works. Correct me if I'm wrong. But let's loop back around to buoyancy, which is fun. Buoyant force is the weight of displaced fluid. And we care about that because we care about boats. And we care about boats because boats are displacing a bunch of fluid. And that fluid that is hopefully equivalent to their... the weight of that fluid is hopefully equivalent to the weight of the boat itself, such that the boat is able to float. That's what floating means. And buoyant force is always directed upward. Feel like that's relatively intuitive, but, you know, just good reminder. And the weight of the displaced fluid is going to be shown through the density, volume, and gravitational acceleration being multiplied together. But, key point here, the whole reason why density is here is just because, like, density is just mass divided by volume. And if we're multiplying by volume, we get mass. So really, the weight of displaced fluid is just the weight that we've already talked about all this time, which is mg, mass times gravity. It's just that we're going to be given the density and volume instead. So we just have to go get the mass ourselves. Let's see. So density is here, also because we want to shout out liquid extraction, which is more related to chemistry. There's a separatory funnel, basically, and it's just like, you're just filtering. It's more advanced filtering because it's just like you know that two liquids or two fluids have different densities, and the one that's higher density is going to be on the bottom. So you're like, wait a minute, if I wait for them to separate, yeah, I take it tomorrow. I just can't not study the day before the test. It's just not a thing that I can do, so I'm trying to do that now, but I'm also trying not to like search things up right now because it's like If I can't understand a concept from my map, then it is what it is. We just have to move on. And that's okay. I'll just take the L if that's showing up on the exam, because at this point there's no point in worrying about it too much. So it is what it is. Why do I have you here? Oh, interesting. Kinetic energy over volume. If you ever have to remember that. Once again, we got something replacing the mass, and that this time is the density, because it's being, well, again, volume's right here, so if we were to multiply both sides by volume, we just get the typical kinetic energy. Oh, I don't know why you're saying sorry, because there's nothing to apologize for. I was just saying that, yeah, I am taking it tomorrow. Wait. Okay. So now that we've got that covered, we have enough knowledge. I'm going to ignore osmotic pressure for now. We have enough knowledge to talk about flow. And if we're ever asked about in ideal fluids versus non-ideal, we just remember that the one that can do laminar flow and is not as viscous is ideal, and is not compressible. Whereas non-ideal is the opposite. We have Bernoulli's principle, which is a lot of fun because we just compare the energy equations, basically, between two points in a fluid, points along, the flow. And we determine that the pressure and potential energy, or potential hydrostatic pressure, sorry, which is equivalent to the potential energy, and its kinetic energy should all together be conserved. So all these values on the other side, given what we know about the other point that we're trying to work with, is going to equal the other, equal to that. And we just have to see that what changed, I guess, basically. Like, yeah, hopefully you get what I mean. There's going to be changing values. That's the whole point. Now, notably, pressure unintuitively lowers during an area of high velocity. That we can see with the Venturi effect. I don't remember exactly what it is, but it's most relevant when it comes to syringes and injecting things. You know that in the point at which that there is a smaller cross-sectional area, that there should be a higher velocity, which you would think has higher pressure, because when we use like water hoses and stuff, we notice that when we lower that, when we increase the velocity of water through that hose, we're thinking that that must be high pressure, but actually that small portion of the hose that is that has a low cross-sectional area is actually low pressure, and we can figure that out through Bernoulli's principle. Volumetric flow rate. I mean, yeah, it's just described by cross-sectional area times fluid velocity. I'm not really sure what else we want to say there. The continuity between 2 points along the tube is going to be the same. I said that an ideal fluid would be all of those things combined. So I believe you can get a laminar flow with a viscous fluid. I feel like I have seen that before. It's the combination of these three. Low viscosity, laminar flow, and incompressibility that leads to that ideal fluid description. Okay. We're done with physics. We're done. It's over. Physics is over. Oh god, there's thermodynamics. But for now, chemistry. This is a lot longer than I thought it would be. Let's see. We know that pressure is force across an area. That's what pascals are. And you can see that here. Per area. Force per area. Flow rate is the amount of liters per second. Okay. Okay, let's see. Oh my god, there's so much. I forgot how big this map actually is. Because I just remember it as little chunks. Okay. Well, that's okay. We're just gonna vibe with it. So, we've already kind of talked about this. This is just the relationships between density and moles in atoms. Radioactive decay, we've got some mnemonics here. Beta negative is when a neutron turns into a proton. So negative N neutron. Beta positive, P proton. And beta positive also very similar to electron capture and positron emission. Very similar, like, end result of proton being turned into neutron. With some nuance, but that's, I just kind of like keep this together. Alpha decay. We've got that helium atom without electrons, I believe. 2 protons, 2 neutrons. And gamma, unique because it's just, if something's in a high energy state, it just emits a ray. It just feels like I'm gonna chill out. So that energy that I had stored within me, out of here with a gamma ray. Also, if you want to radioactively label stuff with organic chemistry, or you just want to make sure that the molecule that is, or the label that is radioactively active stays on the molecule. So if you have like a hydride and it's labeled, you're like, or a hydrogen, I mean, whatever. It's labeled, or if it is the label, you want it to be on the molecule. Wow, big stuff. Okay. Atomic radius. Atomic radius and ionic radius. Going to be down to the left of the periodic table in increasing value, which is the opposite of the ionization energy and electronegativity, which want to keep the electrons together. Ionization energy is like the atom screaming, "No, don't take my electrons." Well, electronegativity is its attraction to those electrons, how attractive it finds those electrons. And we can expect that to be inversely proportional to the radius because the guys with the higher energy wants to keep those electrons closer to the heart. It's been in every single practice exam? Wow. Huh. Is there anything to add to this? Because is it just a matter of remembering what each of these radioactive these different decays are, or is there something more specific to that? Ionization energy is to the right. Yes, okay. Yeah, ionization. So, sorry. I must be, like, really confusing to people that are just listening to the audio. But, my map is more eloquent than I am. I meant to say that up and to the right is when you see more electronegativity and thus a higher necessary ionization energy for the first ionization. Bond length. And YouTube has a like react thing that makes it really hard to see. Okay, there we go. Bond length. Do I have a section for bond length? I should. I'm pretty sure that's just a matter of like, if you have, for example, a double bond and a singular bond, you'll see that the double bond is going to be shorter just because it's like, you can just imagine that the atoms are trying to hold each other closer, and that's why they have a double bond kind of thing going on. Unless, oh, wait. There's a bit more to it. I can see it. Wait, okay, I'm getting a little... Wait, where am I? Oh, right, okay. Bond length, I don't... Again, like... Let's see. I think I'll get to that... No, I don't have a section specifically for bond length. Although I probably should... I probably could review that. Oh, yay. Discovering things that I could review. I'm not really sure what you see, Haley, though. Like, are you talking about a specific thing, or... There... I don't see the bond length specific section. But yeah. Okay, so let me just make sure that we're still working through this. So, electrons. We've got electrons. We got their ground state and an excited state. I mean, yeah, you put in more energy with the photons, so it becomes more excited. Yeah, the bonds more rigid it is, the more stable. Yeah, between a double bond and a single bond, yeah. More bonds. But I'm not really, I don't remember exactly what, how that describes bond length. Which is why I wasn't sure how to answer your question, personally. Because I believe that there's like, it's not as simple as the bonds being stronger, being shorter. There's something else to it. And I think it's more related to the shape of the bonds, or to the shape of the orbital shell, which describes the shape of the bond, kind of. Because when you have a pi bond that's overlapping the two p orbitals, they connect in a double bond. Okay, wait, I'm getting ahead of myself. Or electron orbitals. So we got those shells. We got those quantum numbers, which are described within the shells. And the Aufbau principle is just making sure that you fill in each of these energy points with 2 electrons per like pocket. So in each orbital shell, yeah. And it zigzags along like that. Bond length is proportional to atomic radius. We did it. We freaking did it. Amazing. Is that as simple? Like, okay. I mean, if that's true for single bonds, right? Yeah. And then is that true for other types of bonds? Because I can't really remember off the top of my head. But it's good that you got it. A bit late for your test, I guess, but it is better late than never. Good for my test and other people's tests too. If people are still watching that are taking it tomorrow, or maybe I've stressed some people out because my explanations aren't perfect. So that I can understand too. It should just be a chill day for everyone that's taking it tomorrow. Yeah, so this is the shape of the molecule, or like the bond, the 3D shape that is produced by the bonds from a singular atom is what all these are. Okay. Okay, so these are the amount of valence electrons, basically. So this is just like 1, 2, 3, 4. And that's just kind of like a thing that you might want to know. Bond strength is different. Okay, yeah. I see what you mean. Okay. Yeah, because I vaguely remember something in OChem where I was like, the bonds have very unique properties that are related to their length and strength. I just couldn't remember what they were. Okay, so core electrons have some partial shielding. So we got Zeph with the nuclear charge and the shielding constant. Valence electrons have Lewis dot structures, or are described by Lewis dot structures, and have a formal charge for the molecule. We want 8 valence electrons per per atom, so that's octet rule. And we've got the ions that are they just have a charge because they're missing an electron, or they have an extra one when they shouldn't, or when they wouldn't normally do that. Yeah, stuff like that. And that for that is related to coordination chemistry, just because we have metal ions that are attaching to ligands, and they form coordinate bonds, which are kind of like some kind of bond beyond covalent and ionic. It's just some kind of unique bond where they're kind of like structured around a singular ligand, or a singular metal ion, I believe. And that produces our complex ion. And the coordination number is just referring to the amount of coordinate bonds within that structure that is produced. And of course that is related to ionic bonds, or ions is related to ionic bonds. And if we were to describe the ionic character of the bond, we would check the difference in electronegativity between the ions in question. Okay, let's see. Yeah, wow. This chunk is already out. So we covered this chunk. Now the question is, which way do we want to go? Intermolecular forces are kind of on their own, so let's just quickly look at that. Also, yeah, you'll notice that I love rainbows. It's just perfect for seeing, for differentiating between different elements in the map, and it just looks really nice. And also, well, it's a bit late for Pride Month, but you know, it's cool for that too. But yeah. So London dispersion. You'll notice that I typically use red to mean like lower value, or either a lower number in terms of, in this case, force, or sometimes it can be a higher number if it's just kind of like the intensity of a thing. I wouldn't read into it too much, which is also why I advocate for people to make their own mind maps, because what makes sense in my head will not make sense in yours. But in this particular case, red is meaning low London dispersion. And we got the dipoles. And of course, hydrogen bonds is a very specific dipole with hydrogen. Thank you. I really, yeah, I worked so hard on this map. The only issue is that, like, it's one thing to make the map, and it's another thing to have it memorized. Which I just do not. But it is what it is. We're going to shout out chromatography in this particular section. TLC has a stationary phase that is polar, which means that polar things are going to be slower in it. And to it's Pride Month somewhere. I'm not sure if that's how that works, but, or if that's true. I don't know. But it's always Pride Month, I guess. You know what I mean? There we go. What was I? Oh yeah. Yeah, so the reason why it's yellow along with nonpolar. I'm gonna stay in the photo. Yeah, that's why polar molecules will be slower. Because there's a nonpolar mobile phase, which means that nonpolar ones will be moving a lot faster. And reach the end of the chromatography, or will be a lot further along chromatography at the point at which we measure it. Okay. We can hop into acid and bases. Okay. I have a thing here that I don't remember. Aldols are basically aldehyde and alcohols together. For some reason, acid and bases catalyze those condensations. Don't remember why, I just have that here. But acid and bases, here are some definitions. Arrhenius really just cared about what those look like in H2O. My guy was going super simple with it. He was like, yo, if there's protons in H2O, in water, then it's an acid. Meanwhile, Brunson-Lowry put it one step further and was like, okay, but that's because the acid is giving out the hydrogens. And then Lewis was like, okay, but like, if we think about it with electrons, actually, the reason why well, not the reason why they're donating protons, but if we think about it with electrons, we get that they are accepting those electrons, and that might kick out H's. Yeah, all right. Okay, so with that said, we can figure out that, well, we can talk about acid dissociation, because, as Brunson-Lowry put quite succinctly, thank you, Lewis, shout out to Lewis, but Brunson-Lowry was talking about hydrogens dissociating, right? So we're like thinking acid dissociation, we need a constant for that, and that constant is this. And the pKa of that is the log of that, I think. I'm not very good with logs. I think P basically just means log. And we also know that with pKa, that is the pH at which the protonated and deprotonated are in equal concentrations, which we can see with the relationship of pH with pKa over here with the Henderson-Hasselbalch equation. And pH is, of course, the... I always remember it as like inversely proportional to the amount of hydrogens that there are in the solution, because negative logs are fun. That's all I really need to say, I feel like. Negative logs are fun, and pH is like that because it feels like that. And I always get a little bit confused sometimes whenever I see it show up. And they're like, hey, what's the pH of this thing? And I'm like, oh. It has more, it's a bigger number, so I would imagine more. But then it's not how that works, but it's fine. Anyway. pKa is, as we talked about, related to the dissociation of that hydrogen. So we're thinking, let's name the average between those two pKa's of the first two hydrogens and label that as the isoelectric point. pKa is high and Ka is low for acids. Yes, you're right. I was thinking about... I always get... Yeah. pH and pKa, just great. Let's see. But does that make sense with our Henderson-Hasselbalch equation? Let me see. Acid. pKa of a strong acid is less than 0. pKa is the negative log base 10 Ka. Wait, yeah, okay. No. pKa is low for acids. I think you had them swapped. Because, like, yeah. That didn't make sense for the Henderson-Hasselbalch equation. Because, like, pKa would still be the same as in relation to the pH. It's just you have pH is just the unique situational variation of pKa. Yeah. Okay, okay. Positively charged. Where were we? Protein net charge. It's equal to 0. I have Zwitter ion shouted out here because isoelectric point could have... Well, basically, a Zwitter ion has a positive, or a 0 net charge. It just happens to have 2 different charges on it. That's why it's here. That's all. In any case, isoelectric point is just kind of like, if the pH is lower, that means that it's going to have more availability to pick up those pH or those hydrogens, so it will become positively charged, and it will lose the protons if the pH is greater. I appreciate that. Okay. So, alright, look at that. We've already covered this part of the map, basically, and that's already like a fourth. No, basically a third. Okay, it gets a little denser in the middle, but, well, anyway, we'll get to that in a sec. For the time being, though, I will take a break for now, and I'll return in a second because I gotta go make some food for myself and then maybe grab some tea with some honey or something like that, because I am talking a bit. I don't want to burn out my throat. Not like I'll need it for the test itself, but it would just be uncomfortable. Let's see. How do I change the... There we go. Why is it so... Oh, there we go. Alright, I'll be right back. See you in a bit. Okay, I just realized that I forgot to actually transition to the other scene that said break. So, welcome back from the break. Okay, let's see. Where were we? Man, when I typically make mind maps, like, it's usually pretty easy to follow along, but this one is just, this one's wild. It really, it demonstrates the connectedness of some things, but like, I don't know what this line is for. Functional groups going to oxidizing agents. Yes, oxidizing agents have functional groups. I don't really understand what Pasnik was trying to say here. Anyway, redox. Okay, so redox reactions. We got a reducing agent and an oxidizing agent. Reducing just means that they're going to be accepting the electrons. They're reducing. They become more negative because electrons are negative and thus they become more negative. So, given that, oxidizing agents are going to be tossing out their electrons and yeeting them over to the reducing agent. And we imagine that in a circuit as oxidizing agent being connected to reducing agent by a wire, or, well, wait, why do I have this line here? Not sure why that one's red. Yeah, so oxidizing yeets the electrons along the wire to the reducing, and then we want to make sure that that is a proper circuit, so we have the salt bridge to complete the circuit, and yeah. That's what those, like, I forgot what those are called. Redox, like, tubs with the two metals. What are those called? Redox. No. I'm not gonna search it up right now. It's fine. You'll know it when you see it. Just not need to know what the oxidization means. Okay, so I don't know what a Latimer diagram is. Okay, that I can search up. Okay, well, it's related to standard reduction potential, which is more positive with oxidizing agents and more negative with reducing agents. And the favorability of it being oxidizing is why, like, it's positive. There's also oxidation numbers, which are kind of just, you have to remember them. They're listed here. Oxygen is -2 for whatever reason. Electrodes. Yes. That's what I was trying to explain. Electrodes, which are related to electrophoresis, which is all the way over here on that side of the map. Oh my god. Okay. Let's see. I'm gonna do less of the explaining and more of the pointing now. Because, I mean, this one is just kind of like... Here are the reactions. Here are their names. Here's what happens in them. Combustion's a fun one. Here's our substrates, and blue just means like... Okay, first of all, red means that it doesn't do elimination, like methyl doesn't do elimination 1 or 2. But it does do SN2, which is why it's green. Blue is like resistant, basically. And then this dark green one is possible. And it's just like a matter of remembering stereochemistry for this particular thing. Because like, you know that SN2 is going to be tough for tertiary because it's going to be stereotypically hindered from that nucleophile trying to inject itself into the relationship, basically. And nucleophile is like negatively charged thing that just attacks with its electron sword, basically, trying to step into a molecule, which is fun. Don't know if I can explain any more than that right now at this particular junction of my motivation to explain things right now. This is meant to be more of a tour around the map than it is a full-on chemistry lesson, to be honest. Ooh, okay, wait, so how would I do this? Okay, we're still in... We should probably do physics stuff. So... Okay. Gives free energy. Difference between the energies, energy states of the reactant and product of a, well, reaction, basically. So that's going to be described by a bunch of stuff, including the charges, which is why it would be related to standard reduction potential. But it is also related to heat, and that's where thermodynamics comes in, which was the missing physics section from below. And we have to keep in mind that the heats of combustion just happens to be inversely related to its thermodynamic stability. That's just what it's described as. Because, like, I can't describe it right now. Oh boy. I could do that, it's just, man. I gotta make sure that I don't burn myself out and worry too much about having to be able to explain things right now. So, we're gonna keep it chill. And just show you the overall map. Unchanging processes. These are what they're related to. And that they don't change pressure, volume, temperature, things like that. Latent heat is when we switch between the two, between two states of matter. calorimetry. We've got heat energy here, which is related to specific heat. And that's how much you can change a gram of something by 1 Celsius. And we have the value for water here, for the amount of heat energy required for that. We got heat transfer mechanisms as well. And I was randomly tested on the rate of expansion of a thing when it was heated up. So that was included here. Makes sense. It's changed time by time. It would be proportional to that. Heat transfer mechanisms. Conduction, convection, radiation. Should be straightforward. Sometimes you might get a situation where it's asking about convection or about conduction, and you might think convection because it might be including fluids, but convection is more so like the fluids are being mixed together and stuff. Conduction is like if the molecules are actually hitting the thing and thus changing the heat or changing the temperature. Here's conduction, cross-sectional area for the length of the thing. That's if there's basically like a conducting rod between two objects. That's what this is kind of about. And the two objects are hot and cold. And this is the rod properties. Thermoelectric phenomena. Oh, this one's just kind of... this is extremely low yield. I don't even know if this would ever show up. Basically... two different metals can be intertwined with one another, and if you run a current, or you can make a current with those two metals being heated or cold, and that's what that means. Thermopile just kind of like creates a current from that relationship of being heated and being cold on both ends. There's different types of systems. Isolated is completely isolated, not to be confused with closed, which still can exchange heat. Just imagine it as a cold or as a closed box that still has the outside air touching it and stuff like that. We could talk about catalysts. This is falling more into enzyme territory though, and enzymes we'll get to in a second, so I'm going to loop back around. Actually hit on functional groups, which have this very looking kind of complicated cross shape, but it's actually quite simple. These ones are the simple ones with they're just being a single, double, triple bond between carbons, and alkyl halides just happen to be shouted out here because we have some hydronium ions in relation to that, or like it's being put into an alkane basically. That's why it's here. I don't remember what that is. I'm gonna be honest. We're gonna skim over that because I don't remember. But here are some important functional groups, and you can see that they are labeled with the thing that defines them. So alcohol has that OH. Carboxylic acid. And the reason why this one's in the middle is because the ones to its sides are basically the same as carboxylic acid, except you change one thing, and it's usually not the double bond with oxygen. So you go over to halide if you want to get rid of that O to the side, and then ketone is just in the middle of that molecule. And acetyl groups just have a acetyl. They have a not methyl. They have a carbon. They're on the second to last bit of the thing. They're just short of being a halide. Or an aldehyde. There we go. Enol also has a mix of properties, being that it is... Why is it connected to ketone? What the heck is that? That shouldn't be connected to that. That's weird. Oh, I think it's because you can convert a ketone to an enol, so... But in actuality, it's kind of described by its double bond between carbons and the fact that it has a an alcohol... Oh wait, a hydroxyl OH attached to one of those carbons on that double bond. And we lean over to ester, which replaces that H with something else, an ether. Gets rid of that double bonded oxygen. Amide has the N with something, and then amine just straight up has N by itself. Okay, let's see. We got some different types of spectroscopy here. We got mass spectroscopy, which basically you split a molecule into fragments. You figure out the mass of those fragments. That's where they show up on the map, on the graph. IR spec has different sections for each of the bonds. Just watch out for triple bond. It is the one that's going to be in that second section with the longer bond stretching than double bonds. And I think that's what we were trying to get at with talking about bond length earlier, but there you go. Okay. Stereochem. We got the rules of stereochemistry to determine its clockwise or counterclockwise configuration, which are described by R and S. Highest to lowest priority. When we're facing the lowest priority group away from us. Have this synthesis shouted out. For some reason I had a specific question on that. Don't know why. It's a unique synthesis. It is what it is. Enantiomers are mirror images of each other. And that's related to stereochemistry, but it's also related to the fact that there are enantiomers of amino acids. Okay. Should I cover amino acids now? Or should I switch out? Or should I move to B and B? I don't know. Honestly, yeah, let's loop back around because it's connected to a special pathway that I would like to go over. So I think that's finally it for chemistry and physics for my map for the most part. All right, we did it. We basically did 1/3 of the map. With some explanations missing here and there, but it is what it is. That's just the map that I made, so we're rocking with it. Okay, so we're going back to the MCAT center. And oh look, what does this say? So cars, I can't, there's nothing to share when it comes to cars knowledge. You just gotta get good at it, man. I don't know, just read a bunch, right? Yeah, so I like cars a lot, personally. because it is the exact thing that I tend to watch and listen to and read about, which tends to be critics talking about art, or people talking about various historical things and making arguments for shit. I love listening to all of that, and yeah, unfortunately, if you just aren't good enough at cars, it is what it is. Which is another reason why the test is a bit BS. Oh, well, wait a minute. What is all this? Where did this all come from? It's almost like there's like some video essayists and documentary YouTubers that I would prefer to shout out and let you guys know that if you want to improve on cars, you could probably watch some of these guys and maybe get a glean for that kind of argumentation. I don't know. Including a very wise Viper indeed, who will definitely be making video essays as soon as he takes his MCAT. That will definitely happen. Well, that's cars. Yay, cars. Okay. So this stats part is kind of more psych related. Just wanted to remember, you know, null hypotheses, correlation coefficient, and box and whisker. I always freak out about box and whisker plots because the actual like significant interval is with the funnel part. Shameless. Absolutely shameless indeed. I mean, it would be a great plug if it weren't for the fact that I don't have any video essays on my channel right now. I have made some before, but they're not on the channel right now, so oops. I'll definitely get to that. Alright, well, there's stats. There you go. Defunctland is so good. So good. I love Defunctland so much. Learning how you monetize entertainment basically within the realm of working with a huge like physical location that you have to manage. Fascinating stuff. Okay, so here's my anatomy section, which I did mention earlier. I do have nephrology here. This is very minimalist. Also, again, this is an anime channel, so we've got cells at work characters representing each of the little cells. Cells at work really likes the immune system, specifically. So we got a bunch of these guys here. B cells, T cells, dendritic cells, macrophages, basophils, mast cells, neutrophils, and eosinophils, and natural killers. I'm just not really sure if I've ever seen these tested, to be honest. But they're here, because I just decided that, yeah, I can include them. Yeah, just watch Cells at Work if you want to know about the immune system. Like, I just distinctly remember macrophages like eating the enemy pathogens, which was like really surprising. The way that they represented that. That was brutal. But aside from that, the way that these characters interact with one another is a bit beyond the scope of what I want to talk about today. Well, nephrons, look at that. We got the glomerulus encapsulated within the capsule. And that's exchanging stuff, and it's passing all of the junk over to the nephron to filter out Passively, it filters out water, and actively it filters out solutes when entering the loop. And then here's some other anatomical parts that are involved in that flow, basically. And of course, the junction between the cortex and medulla is where we see the loop of Henle dip down into. So here we go. We also have our EKG for the heart. It's just a matter of keeping track of the fact that the atriums are going to depolarize first, throwing that blood into the ventricles. Then the ventricles are going to depolarize, shoot that blood out, and then they will repolarize to get reset. So that's what this is all about. I forget exactly why the QRS is shaped like this. I think it's just a matter of them getting prepared and then squeezing and then kind of getting reset, except electronically, because this is tracking the electrical signals. So that is anatomy that I have listed here. I could have included like gastrointestinal stuff. I just don't have the space for it right now, nor the time to put it in. So that's what we're working with. We have some evolution shoutouts with okay, how should we cover this? Darwinian concepts, specifically referring to natural selection. We've got those different selection situations in mind. Particularly, we have fitness, and inclusive fitness can be described with the amount of offspring or relatives aided through altruism, which is actually why, like, indirect fitness is actually pretty important in understanding why homosexuality is actually a evolutionary relevant thing to have for certain species, because, like, for example, like bees, well, not bees specifically in terms of sexuality, but in terms of like this indirect fitness concept, the more relatives that you help out without having to worry about your own offspring, that is a perfectly like good explanation for an increase in overall fitness for the genes at play within the relatives that you have, if that makes sense. You can look more into that in evolutionary psychology. It's really interesting, actually. Really, really cool stuff. Anyway, we have some genetic drift happening. That's when random shit happens and some species get split up from other parts of the species and become more polarized in terms of their traits. And species also are reproductively isolated in different ways, either by pre-zygotic, before the zygote is actually formed, or after post-zygotic, where the zygote or the offspring are just not viable for whatever reason to pass down the genes. Yeah. Okay, so BB, biological and biochemical stuff. Okay. This I can explain a little bit better, because it's a lot simpler and just very straightforward than physics and chemistry is when arranged in my head. Because we get to follow this purple line, and the purple line is the central dogma line, the thing that simplifies all of biology to DNA turning into RNA, and then that making some proteins that also happen to make enzymes. I don't think the enzymes are technically part of central dogma, but work with me here. So central dogma determines that DNA is the first stop we make. And DNA has a lot of branches, including a branch that has mitochondria. We're just going to ignore that for now. But DNA has some history to it. Here's some famous scientists that discovered some things about DNA. Shout out to Rosalind Franklin specifically, because I feel like she got totally cheated when it comes to the her scientific recognition during her lifetime, which is very unfortunate, because Watson and Crick are the ones that are credited for the double helix, even though it was Franklin's photograph that led them to that discovery. But anyway, with DNA, we could talk about alleles, which we were just talking about with evolution. Some genetic stuff. Got your phenotype, genotype. Heterozygous is just like if you have an allele that's different from the... You have two alleles that are different from one another. Then you got Hardy-Weinberg trying to figure out that stable allele frequency between those two differing alleles. And there's some assumptions that have to be made in order for this equation to work. And those are noted here. Mendelian genetics can be best figured out through the Punnett square method, but basically there's typically a dominant and recessive version of an allele, and there's different types of dominance that are described here, where complete dominance takes over the phenotype completely, whereas codominant, you get a mix of both, or rather a spotted demonstration of one or the other in different parts of the individual. And incomplete is a mixing, like an actual, like you mixed up the properties of those alleles, and we're like, wow, that is a whole other different, like, colored fur or colored petals or something like that than both of the parents. Okay, we got some technology to kind of parse out information from the DNA. And that includes PCR, DNA libraries, and DNA cloning, hybridization, and sequencing. I feel like PCR is probably the most famous of these ones. It's just a matter of like knowing that you denature the DNA, then you try to put a primer on it, and then you try to extend that primer just to basically work with tiny chunks of the DNA, and those chunks can be ordered accordingly to be sequenced. Oh, and that's why DNA sequencing is right here. I feel like we can even put this over at the end of PCR, but that's fine. That works too. First, genetics has some knockout genes, which are fun in a experimental setting. And some other stuff that we'll talk about is basic blotting, which includes the southern blot for DNA specifically. And southern blot has some radio-labeled DNA, I believe, which you'll put into a gel electrophoresis. Now this is where we have the negative and positive electrodes, creating this charged field that, since DNA is negatively charged, it will move further along the the agarose gel in order to reach the positive electrode. If it is a bigger fragment, I think. Wait. Smaller fragment? That doesn't make sense for me. Larger bands, shorter bands. Yeah. Sorry, it is definitely the smaller fragment that goes further. The reason why I got confused there is just because, like, despite it being more negative, it's not going to be pushed further down. Sorry. Smaller fragments are pushed further. And also note that there is the actual thing that is creating the negative the negative section of the electrophoresis is actually a cathode, because it is taking away the hydrogens from the surrounding water or the surrounding gel. Wait. I think that depends if you have... No, yes. If you have... no, yes. If you have water as the mobile phase, then that is what needs to be done in order to create that opposite charges at the ends. Okay. DNA can be formed into chromosomes, which can be interacted with one another through recombination, and you can figure out some gene mapping through that recombination. And you have some autosomal chromosomes in this section here. Not that I remember exactly how to describe what that means right now. We're just gonna vibe with it. Okay, so when we talk about chromosomes compacting one another into histones, we notice that okay. We notice that heterochromatin tends to work with histone deacetylase, which opens up... No. Which increases the salt bridges, whereas euchromatin decreases them, because they will break them open for the acetylation. And oh man, I'm already getting a little bit burned out. Give me 1 second as I kind of like resettle myself. Okay. So the salt bridges are what is blocking transcription from happening within the histones. And so when we have the histones with like acetylified, we transfer out the possibility of forming those salt bridges, and therefore lowering those salt bridges or destroying those salt bridges, we are more available to transcribe, if that makes sense. There's also some other forms of inheritance which we'll loop back around to later. So in order to transcribe stuff, you tend to have various different structures within the DNA sequence that allow it to be easier to find and activate find and activate the sequence that needs to be transcribed. And you have different operons, which are just different sections of the DNA, to make it a bit easier to see what needs to be... Like, basically, these are the different sections that are going to be... oh my god. I'm blanking on how to describe that. Like... There's just different... That's just... Wait, what? Hold on. Control region... Operon... Does that include... Okay, it doesn't include the regulatory gene. That's what I was trying to figure out. Okay. It is just the section that is being promoted and operated on to create the structural genes, or to create the mRNA from the structural genes. So there you go. Okay. All right. We got some enhancers or silencers. And we have RNA polymerase, which is interacting with the template strand in order to pretty much match the coding strand, with the exception of uracil replacing thiamine, or thymine, sorry. Oh, it's literally right here. And so that becomes pre-RNA, mRNA, and that enters into the spliceosome, which splits out the introns, and we keep the exons. Okay, I'm going to finish this real quick. We have the 5' cap, which is basically just put a guanide in that 5' position at that end, whereas the poly A tail is on the other 3' with a bunch of adenines to make it less likely to get destroyed within the cytosol as it travels. I guess, something like that. So we get to mRNA, but before we do that, we actually have a bunch of different sections of DNA, which includes some forms of mutations. And here's an assortment of mutations along with their more basic formats, like base substitution. It has actually like 3 different variations to it, including frame shift as well. And you might see some large-scale mutations when the DNA segment can like be flipped over and stuff like that, or just moved altogether into a different part of the DNA sequence for whatever reason, from very severe large-scale damage, or just like accidental just shifting of stuff. And for the different mutagens, we have some exogenous and endogenous ones. Exogenous, I actually forget how to describe these two subspecies of that. But ROS, we know, tends to be from the end of the electron transport chain when oxygen species just kind of form but aren't utilized in a different like segment, so or a different like reaction, so they end up interrupting DNA a lot and messing with it a lot. So that's what we have to worry about when we want to use. It's the reason why we have antioxidants and we want to use those, basically. Mutagens, we of course have to think about cancer a bit. Cancer has a bunch of things going on. Let's see here. I think this is just describing the creation of a oncogene, which is basically like a cancer creating gene, I believe. Has been a second since I've written this portion specifically. But all of that is included within the concept of DNA damage. And senescence is DNA damage when just over time, as you get older, you get some senescent cells, which are basically like useless cells because their DNA has been damaged to the point where they're just not really doing anything. They're not the same as cancerous cells, though. They're just kind of chilling, just doing nothing. Apoptosis is the, well, basically cells killing themselves. I'm not 100% sure why I connected that over to DNA damage, but it's here, so shout out to that. There is a form of DNA repair, which includes mismatch repair, which requires some proofreading with some activity from an endonuclease in order to fix the mistakes of DNA polymerase 1, I think. RNA primer, wait. Exonuclease. Moves successive nucleotides from the end of a polynucleotide molecule. Oh, wait. Okay, I see. This is basically cutting out the problematic part and utilizing polymerase in order to rebuild it. Or wait, right? Yeah, and so that's utilizing polymerase. Okay. Oh boy. Sorry if I'm not explaining things properly. It's just kind of like trying to assemble the explanation in my head is a lot harder than being able to just read it. Because these are not your usual notes where you can just like explain stuff. It's just kind of like the connections will lead into one another somehow, which is why I tend to have these little like this stuff that helps explain stuff later. To explain the note. Anyway, okay. So we got different nucleotides, and these are the different names. This is the actual name of the base, and this is the name of the base plus the rest of it, the rest of the sugar, basically. So deoxyadenosine will be the deoxyribose version of adenine, as opposed to the simple ribose version, which is just going to be adenosine by itself, I think. And on the 5' end, you have the phosphate group, which is negatively charged, which is why it moves along the gel electrophoresis. Purines we remember as pure as gold, and they have 2 rings. Okay. Going back to mRNA, so that we can continue on our central dogma pathway. Okay, we're really working through this. Nice. We got to consider translation. And there are specific codons that we will be utilizing in the ribosome in order to figure out what amino acids are going to be formed on this chain to build that protein that we want. And ribosomes have 3 different sites, an A, P, and E site. A site is basically where you enter. P is actually where you get connected with tRNA. And there's a Wobble hypothesis which proposes that the 3rd nucleotide in a codon is actually not that strong of an indicator of the amino acid that is being selected from the tRNA, which basically has a amino acid attached to it, which is why it's being connected to the ribosome. I'm missing something here. What am I missing? I think RNA is the thing that's missing, right? RNA, ribosomal RNA? Or no, rRNA forms the ribosome, I'm pretty sure. No, yeah, it's still reading from the mRNA to connect to tRNA, which has an amino acid stuck to it. Yes. Okay. And then it's ejected in the E site. Okay. And so we just dip into amino acids, which, wow, this section looks a lot more of a mess now that I look at it from afar, but is actually quite simple. We've got your nonpolar and your polar amino acids. And in our nonpolar section, we have the alkyls, which includes valine, leucine, isoleucine, glycine, proline, methionine, and alanine. And we've got a bunch of different mnemonics that I use to remember, glycine being the most generic one in my mind. And alanine just has like that random carbon atom. Valine is V-shaped, coming off of the actual amino acid itself. While leucine has more of a Y shape, and it's just kind of like well, basically, in order to remember the difference between isoleucine and leucine, I just think of the next, like, first letter of the next word in the statement, I love you. So love you is leucine. And then Isoleucine is more of an L shape. So it's I love. And then I love Amelia just because it's like the 3-letter name for isoleucine is ILE. So that's how I remember that. Methionine is missing meth. We miss the seasons of Breaking Bad so badly that we have a sulfur in the 3rd position along that chain of carbons. And proline is like pro gaming pentakill from League, even though I don't play League, but it is a very memorable meme. Got our aromatics, tryptophan, which if you've ever played Xenoblade 2, this is a Malthus, and he has tripped up his dub because he really screwed up during that game, and he also the nation that he leads, or I think the giant that lives that his nation is built on, is called Indol, and he also looks kind of like an Indol because of the bigger like forehead and smaller kind of like face shape. Phenylalanine, chemists can't spell F, so we get F. That's to remember the fact that its letter designation is F for whatever reason. And if you add a hydroxyl group to phenylalanine, its little like ring thing, you add a hydroxyl, then it becomes tyrosine. And tyrosine is amongst these more neutral or the neutral amino acids within this polar section, which includes serine, threonine, and asparagine. And serine, I remember more as like Selene is an alcoholic, and they're throwing back the alcohol to their throats, I guess. Hard to explain that exact mnemonic, but yeah, that's how I remember it. Asparagine, just remember acinine, asparagus, and glutamine. Has an amide actually. And then you switch out that amide for, or that, yeah, that amide, we'll say amide, for a carboxylic acid to get the glutamic acid, which is the same as doing that with the asparagine, just because asparagine is just the shorter version of glutamine. And cysteine is the special one that has a thiol, and in a oxidizing environment, it forms the bridges, the famous disulfide bridges. On the acidic side, we got aspartic and glutamic acid, and that also leads to aspartate and glutamate, which are the versions of these two without the H's on the end. You lose the protons. And these are all negatively charged, including tyrosine and cysteine. Then we get the basic. And here's lysine, which is involved in ubiquination. And the shape of it is, well, you killed someone with the Sword of Lies. And the Sword of Lies is basically, if you imagine the pommel being the amino and carboxylic acid, you have the sword formed by a bunch of carbons and leading into a nitrogen at the end. Histidine is an imidazole, or has an imidazole. And that just reminds me of proline's shape, but with two N's, which makes me think that they have a history of saying some pro-gamer words. So histidine, history. Oh my god. Meanwhile, arginine has looks like a fork with the two N's at the end. So it's two-prong fork argument. R or arginine. The stereochemistry of amino acids are represented here. Okay, so if you turn basically left from the top of the stereochemic circle that is formed, which would be counterclockwise, you get your L amino acids. You get your right ones from the opposite side, which shows up as spinning in those directions, those given directions, in a polarized light. Also, racemic just has 50-50 shape or amounts of those. Okay. So, in your first degree formation of a protein, you're working with peptide bonds first. Then in the second degree, you got alpha helices and beta pleated sheets. Then you're working with folding the protein together. And if you're lucky and have a polypeptide work going on, you end up with a bunch of subunits that will be attaching to one another, and you get the different mers, or well, sorry, the polypeptide is just a protein. Meanwhile, the subunit folding or addition in that fourth degree is adding together a bunch of subunits, and they are stable within very specific temperatures and pHs. Proteins were blotted with the Western blot, and if you remember south and north blots, which south is a RNA related one, then you'll remember that the combination of those will be how they interact. Page is going to be denaturing proteins with SDS, or yeah, if it's SDS page, then we would use SDS, which is an anionic detergent, to denature proteins, which can also be a reducing SDS if you're reducing the disulfide bonds, breaking them apart, and separating all the subunits. You got the different protein functions that are not enzymatic in this section, which includes some cell adhesion molecules. I don't have all of them here, unfortunately, but Bao integrants. I just Bao is kind of a saying from a twin from some VTubers that are twins, and they grin a lot, so I remember integrins are just twins that are attaching to things. Then you got your transport proteins
and there's different variations of how they work. These ones are pretty straightforward with the exception of secondary active transport, which is just kind of like they use a molecule to help the target molecule going down from its gradient, and sometimes they can go different directions and stuff like that in order to like swap places and stuff. You got your motor proteins, including myosin, which is related to muscle contraction, and that has kind of a loop where you have the cross bridge formation in the resting state, or the cross bridge formation formed from resting state with the help of calcium. And once that phosphate is released, the Cockton-Reddy formation turns into the power stroke, and then it yeets out the ADP, and now a new ATP is taken in and hydrolyzed so that it goes back into that cross bridge formation. Antibodies have different sections, but the important part is that it has a paratope that will attach to the epitope on the antigen. Different protein modifications, which I could have colored, to be honest, but we're just not going to bother with that right now. Dealing with a bunch of different possible modifications to protein. They're listed here. We also have another set of chromatography, which includes affinity, size exclusion, and cation exchange. Man. I'm just gonna not explain too much right now. We're just zooming through here. Cation exchange is the negative, the negative beads. And so cations would get attached to the beads and not fall immediately. So that's what that's about. Anyway, GPCRs got the different G alpha subunits, lead to either working with or against adenylene cyclase. And the gist of a G protein GPCR is that a G protein is signaled to launch from its spot and move over to the enzyme being activated so that it sends down a secondary messenger and creates that signal transition cascade with the expectation of a cellular response. All right. We got enzymes. There's different types of bindings, including allosteric, which is off to the side and not on the active site. So that's what allosteric is doing over there. An active site will have our substrate enter that active site so that sometimes it induces a better fit so that it turns into this transition state. But the thing to remember with enzymes is that it's just a catalyst, a very special type of catalyst that just happens to be a protein. Lowers the activation energy so that we can get over that hump and actually activate the reaction. And there's different strategies that allows that catalyst to be more effective, and enzymes can do this stuff, basically. going back over here, we have some cooperativity to consider. Positively cooperative ones going to be an S-shaped curve, while no cooperativity is hyperbolic, and negative is just lower Vmax and higher Km. Which is basically this graph is kind of like stunted like that. And they match their Hill coefficient, except for the fact that the reference point is not 0, as one would expect when we're talking about negative stuff. It's 1, so anything less than 1 in Hill coefficient is negative. Two substrate reactions can have two different ways of dealing with them, including creating a 3-molecule complex and ternary complex, and a ping-pong solution where substrate 1 binds and makes it better for S2 for substrate 2, and then S2 just makes it easier for S1, and then the cycle goes on and on. Vmax, what is that? Well, let's talk about rates. So the maximum rate of a enzyme occurring is called Vmax, because at some point the amount of enzymes that you have that's just the top speed of how they're going to produce the products that you want. And so Vmax is top speed, while Km is kind of like this constant that we figure out to see at what point we reached halfway up Vmax, which is kind of like if you were imagine a car, for example, as if it were an enzyme, that would be its 0 to 60, kind of, except in this case it would be 0 to half Vmax. And the thing is, manga guide to biochem said this, Lineweaver and Burke, eat your hearts out. But specifically, the reason why we turned this Michaelis-Menten equation into Lineweaver or Burke is so that we can actually make it a lot easier to figure things out, because working with reciprocals is a lot easier than working with a big ol' loop, big ol' hill that we have to wait and see where the Vmax is, when we can just find Vmax by doing reciprocal, because we know that the if we were to turn everything into reciprocals, Vmax is just the y-intercept. Well, reciprocal of the y-intercept. And x is -1, the negative reciprocal of Km. And there's different types of inhibition, which I remember with these 5 idiots from Kanojo mo Kanojo. I don't think if you don't know the manga, basically, oh jeez, there basically is 4 different girls competing for one guy, except they have different personalities and stuff. So this one is very competitive. I just remember her being uncompetitive because she's just a lot like, she shows up first and is very chill and doesn't expect the relationship to go very fast, so that's why Vmax is low, but Km is low because she shows up at the start of the story. And Saki over here unfortunately hinders her Vmax because she allows oh god, I'm blanking on her name, blue hair girl to show up and change up the relationship. And Vmax just very low because she's not a very competitive person. But her Km doesn't change because she was already there at the start of the relationship. And the inhibitor is just kind of like not being like it's a very weirdly intuitive and unintuitive thing. Inhibitor kind of binds and unbinds equally, so the KM is just kind of like not changing that much. It's a weird thing happening over there. Competitive, gonna eventually reach Vmax, because like, just because the inhibitor is stealing the spots from the substrate doesn't mean that it's gonna slow the overall maximum capacity of the enzymes down. It'll just slow the make it harder to reach that point, just a little bit more difficult. So lower Km. Wait. Substrate. Oh, whoops. I think I explained something on blue and on competitive. It's lower Km. Yeah, because she shows up earlier in the story. Yeah. Substrate concentration shows up very quickly, and so competitive also shows up very quickly, but doesn't hinder the overall velocity or rate. Whereas mixed is like a bit of both non-competitive and just like with a better inhibitor, basically. So it slows down the Km. But the Vmax stays relatively the same for mixed. Mixed is an unusual inhibition style that I don't really see too much, but there you go. Okay, so we've already kind of talked about rate, but rate can be described by being multiplied with, or being the multiplication between a constant and the concentration of something, of the concentration in question, I mean. And we have some rate steps here for the enzyme and substrate binding, which is described as the rate law. And the reaction order is just the sum of the exponents of that rate law. So it's the, yeah, it's just the sum of the exponents. That's the easiest way to explain it. And the rate constant can actually be found with the Arrhenius equation, which something that I didn't really know existed until I was trying to figure out what rate constant actually was. And it's this. Yeah. And that deals with the activation energy being divided by the gas constant and temperature within the context of frequency factor and exponential factor, but if that shows up on the MCAT, I'm pretty sure they would tell you what these would be, and I don't think you would actually calculate that. It's just a thing that if you're curious about it, there it is. Okay, so enzymes have coenzymes and cofactors that help to stabilize things, make it easier for the the reaction to occur. And there's different types of enzymes included here: transferase, ligase, oxoreductase, isomerase, and hydrolase, and lyase. And these are going to be relevant in, well, not protease. Protease is just when you destroy or break apart a protein through hydrolysis. but dehydrogenase and kinase are going to be relevant in glycolysis and stuff. Okay. I think we did it. We looped all the way around. So that is BB completed. And I know that I'm skimming through some stuff because like I don't want to overwhelm myself. And I have to keep in mind that this anxiety of teaching the stuff is going to be a little different from my test anxiety, hopefully. So I will be better at connecting the dots on the test, hopefully. But this is just good review just to make sure that like I remember the connections that I have made previously. And cognitively speaking, that is the most similar in encoding strategy to what your brain actually does when it tries to learn, like associative learning, basically. It increases the connections between the synapse and the like forms those synaptic connections to represent those concepts, essentially. And so that's the ideal situation with creating these mind maps, is that I actually make a mind map within my mind that is close to whatever this is. But honestly, if I were to need to take the test again, I would probably need to revamp this map because there's just a lot of extra things that are kind of getting in the way, or the actual organization of the map is a little bit of a mess. But that's just a thing for future Nick to figure out if he wants to figure that out. For the time being, we're looping all the way back, thinking about extranuclear inheritance. So DNA doesn't actually, the DNA in your nucleus of the cell, not actually the only piece of inheritance in a cell. And that includes mitochondria or chloroplasts, which you would get from your mother. And chloroplasts we won't really talk about too much because MCAT doesn't really care about plants. At least I hope they don't, because I am not interested in botany. But thinking about mitochondria, there's different things that regulate whether glycolysis or something else happens. And that is insulin versus glucagon. And you'll see that when insulin is affected, it'll increase the function of phosphofructokinase, PFK2, which will which will create fructose 2,6 biphosphate to indicate that they want to do glycolysis to further turn fructose 6p into this fructose, which utilizes some ATP to do so. And that is part of a chain called glycolysis, starting with glucose that we get from our food. Speaking of which, okay, glucose is a monosaccharide. So we know that there are different epimers of monosaccharides that would make glucose actually galactose instead. And we want to note that glucose is also an aldohexose. Hex as in 6 carbon atoms. And we get these sugars from, well, okay, basically sugars are carbohydrates. Carbohydrates have rings. Rings are, rings tend to have anomeric Cs, which have 2 oxygens connected to them, assuming that it's a closed ring. And that linkage between between saccharides can form disaccharides or polysaccharides, and they're formed here. Glycosidic bonds, you can make a really long chain with those into lipids. And there's either non-hydrolyzable ones or hydrolyzable ones. And triglycerides are the ones that we want to think about because those are the more notable of the fatty acid chains, basically. I think, hold on. Yes, okay, so triglycerides have this glycerol backbone, and there are 3 fatty acid chains on them, I think, is what I was trying to go for there. So hexokinase into glucose 6P, and this phosphoglucomutase, which you're just kind of like converting into fructose. If we follow glycolysis, aldolase is going to try and change fructose 1,6-biphosphate. And you either get one of these two, which will always typically end up with glycerolide 3-phosphate. Dehydrogenase, whenever we see that, we know that we're going to be forming NADHs. Oh, ketone, I think I'll take that out. Meanwhile, whenever we see kinase in this particular chain of events, we'll think that ATP is being formed. And we're going to ignore the fatty acid stuff for now and just continue on. Mutase just changes up the 3 to 2. Enolase is how we make PEP. And pyruvate kinase, again, kinase, taking out that ATP, throwing it into the stratosphere to be included in the final count of ATPs that we make. Pyruvate. And we just got the Krebs cycle. I mean, this is just me trying to describe the Krebs cycle. It's just nice to have it color-coded, though, so that we have the dehydrogenases forming the NADHs, and or the FADH2 that is made from succinate to fumarate. And yeah, just loop back around. We do this 1, 2, 3, 8 NADHs per pyruvate. So if we were to count that up, we know that there are 2 pyruvates per glucose, so we would multiply everything by 2, basically. And we know that for the, well, this is just describing what I was explaining with dehydrogenase, that it creates the electron carriers, which will be used in the electron transport chain right here. Complex 1 is NADH related, and FADH is for complex 2. That creates ubiquinone, loops back around to complex 3, making that cytochrome C. and also pushing those protons over to the intermembrane space. We use oxidase to create water. That's why when we breathe out, we breathe out CO2 and also some water molecules. If you think about metabolism that way. And then chemiosmosis is what pushes ATP synthase to physically push the phosphate onto onto ADP, and we notice that it's kind of got this efficiency of 3 protons being 1 ADP to 1 ATP conversion rate. And so if we do the count, it kind of ends up like 32 ATP for electron transport chain, but depends on the textbook that you use. That's just the ones that I used. But we know for sure that glycolysis and Krebs are releasing 2 ADP each. Not that I have labeled that in the Krebs cycle, but I have labeled that in the glucose one. Where is... Oh, okay. And Krebs cycle is a aerobic process. An anaerobic one would just be the formation of lactic acid, because we've made some NADHs along the pathway from glycolysis, and now we're freaking out because NADH likes to be turned into NAD plus eventually, and it can't do that if we don't have any oxygen for the electron transport chain. So there are a couple things that make acetyl-CoA. We can break apart proteins into their amino acids, and that can be formed into acetyl-CoA, or we can do a different process. If acetyl-CoA is floating around in the cytoplasm, we use acetyl-CoA carboxylase to make malonyl-CoA. And this is inhibited by AMPK, which is basically a detector for AMP in the cytoplasm. Just going like, hey, wait a minute. There's a lot of AMP here. We don't need to be making malonyl-CoA, because malonyl-CoA is triggering this, which flows across the mitochondrial membrane and would trigger beta oxidation, which creates more acetyl-CoA. So if we inhibited this, wait. Sorry, malonyl-CoA inhibits this. So if we inhibit this, malonyl-CoA would no longer inhibit the creation of acetyl-CoA. But if we were to allow this to go, wait, hold on. AMP is demonstrating that there was a lot of usage of ATP, and so this body is freaking out because it wants more ATP. So how can we get more ATP? We want more acetyl-CoA. And so we would inhibit this to decrease this, to decrease the inhibition of acetyl-CoA creation. Yes. So that makes sense. So body is freaking out about energy over usage needs more acetyl-CoA. So that is what that end product would be. And if it doesn't care, then it'll be fine with inhibiting the creation of acetyl-CoA. And instead we'll allow fatty acid synthesis to occur so we can have more compact energy stores for the future. And so we make those triglycerides. All right. Okay. We're finally done with biology and chemistry and physics. And now we have a lot of psych-soc to do. But this one we can just chill out with because I love psych-soc. I would love to just kind of vibe with it. I want to shout out, though, before we move on to psych-soc, some of the stuff that helped me with psych and chem and, or sorry, with physics, chem, and bio. We got all these assortment of lovely people, including an amino acid song, which I recommend giving a listen. It's fantastic. And if you want some memes, Cinephile is great for that, but it's not actually like one of the others that are a little bit more succinct in their explanations for certain concepts. So yeah, just shout out to all these guys. And be sure to include any shout outs that you would like to add to the comments below so that I can check them out, because at the end of the day, I do still like science, even though, you know, it gets a little bit complicated here or there and gets a little bit mushy in my mind sometimes, but that's okay. All right, psych-soc. Let's do this. All right, psychology. First, begin with the brain. Begin with neurobiology. Got different neurons. Active transportation, we gotta make sure that we're trying to maintain the bananas in the sea. Those neurons gotta keep the sodium out and the potassium in, so that when we have that action potential, boom, we can cross the barrier. And of course, we got the leak channels, so that it's very similar to that salt bridge in redox, actually, in that it allows that electrical circuit to occur. I call it circuits, but I think there's a different way of explaining that. Let me know if there's anything like that. Anyway, let's go to perception. Got different receptors that allow you to perceive different things. Taste, temperature, and auditory. And the one that is pretty cool about auditory systems is that after the vibrations pass through these three, it enters the cochlea and moves the basilar membrane, which shifts around the mechanoreceptors. Registers in the hair cells as sound to you, and you interpret all of that based on the placements of those cells and their vibrations. Balance is regulated by the semicircular canals, which are basically like a bunch of semicircles that are in different orientations that allow you to recognize when there's a kind of like pressure shift when you tilt your head to the side and stuff like that, allowing you to balance yourself out, as well as some other means of creating balance, which includes proprioceptors, which is how you feel where you are in terms of balance, and visual input. I mean, that's kind of evident through vision. And you got photoreceptors, and we've already mentioned rods and cones. In order to understand the distance of things, you usually use the disparity within your retina between the two retinas to figure out how far something is. Your brain makes that calculation for you. Ciliary muscles just kind of helps with that concentration, that focus, in figuring out the distance of that visual object. And then here we get into the calculations your mind makes in order to interpret visual information. Utilizes the constancies of different things to understand what an object is and what it's shaped like and how it exists. Like, what is it? And the Gestalt principles in particular allow you to utilize more abstract, like, visual phenomena and form a cohesive image from that. And you have like your contours that kind of helps you like figure out if something is hidden, kind of like. Let me show you. Is hidden kind of like in this assortment of negative space, basically. Stuff like that. Multi-stability. I actually don't remember that one that well. Yeah, so multi-stability is just like you can see two different images from one visual input. Makes sense. And this is your depth cues. Kind of like imagine this as a road, linear perspective. The road kind of like converges on itself, but you understand that to be a straight line. And we can figure out the distance we are from certain things based on certain cues. Yeah. Perception has some other things involved too, including absolute, well, basically, if we want to detect a signal, there's the absolute threshold, which we'll find every 50% of the time we'll be able to register that a stimulation has occurred, whereas difference threshold is more like you can compare two stimuli, and at which point we would figure out that they are different. Well, that's the difference threshold. And I noticed that I have these two together, but I feel like they are referring to different concepts. Minimum required difference between. Okay, that's why. Detect. So it's really more like this. This is the relationship between difference threshold and absolute. There we go. It's like the 50% of the time for the just noticeable difference. Orientation. We just went over this, actually. These two are just referring to proprioceptors and semicircular canals, respectively. All right. Got your neurotransmitters. and be right back because I'm going to go to get a drink. We're almost done here. Almost done with this tour across the map. Don't I have a be right back screen? I thought I had a be right back. Why do I not have a... Okay, well, whatever. Give me 1 second, I'll be right back. Neurotransmitters. All right. Got your mood stabilizer, serotonin, pleasure reward center, or neurotransmitter, dopamine. And it's also semi-related to endorphins and oxytocin. Oxytocin, which is kind of that love hormone. I mean transmitter. Acetylcholine is incredibly important to neuromuscular junction, or to the function of your muscles, essentially. Glutamate tends to be a not inhibitor, a promoter, and GABA tends to inhibit. Epinephrine is kind of your adrenaline related kind of neurotransmitter where you're more alert and at attention when they are present, along with norepinephrine, which is basically epinephrine's cousin that also is just in the brain as opposed to epinephrine being everywhere else. And depression, the monoamine hypothesis suggests that all three of these guys are a complete mess, which is why depression occurs, it is present, basically. Yeah. Got your brain structures. Prefrontal in front of the frontal, parietal on top, occipital for that visual processing. You gotta draw that line from your eyes all the way back to your head. And that temporal lobe is more for listening and auditory processing. Cerebellum is just more of that motor learning, that posture, that coordination stuff in play. There's also left hemisphere and right hemisphere. Left is a lot more logical and analytical. Right is a lot more expressive and emotional. So there's that. Got your limbic system. I think this might be particularly interesting if you're researching about stress, hypothalamus, into the pituitary gland, that HPA axis, kind of messing with the autonomic nervous system, in that if you're stressed out, you're going to activate more of that sympathetic response when you don't really need to fight or flight, and in actuality. And yeah, we got the primary emotions in the amygdala, memory consolidation in hippocampus, and thalamus is a relay center. Oh, I was just mentioning stress. So here you go. Sympathetic is activated and parasympathetic is impaired. And over the long term, it can mess with all these sorts of things. There's also such a thing called the general adaptation syndrome, in which case there are kind of 3 stages, but these are generalizable stages to different types of stress. That's kind of the idea behind this adaptation, because we all have similar ways of adapting to that stress, and it takes the forms of these 3 stages. Where we initially freak out, we kind of get used to it, but then we just get so tired of it. And if you feel burnout, I think this is where you are in that stage. And I'm feeling a little bit of burnout myself. Hopefully I'll be okay during the actual test. But I think it's more so burned out of studying, so I'll just cruise through this section, and thank God I can, because this section is very it's the most straightforward of the sections when it comes to cruising through, because we have this long highway all the way up to neurobiology, and as we move down, we get a little bit further and further away from neuro and into the psych section. But for now, we have to think still in terms of medicine, biomedical approach. We tend to treat things with medical treatments, and we assume that physiological causes are presenting these psych symptoms, which may not always be the case. But in the case of schizophrenia or any psychotic disorder, we have neuroleptic medications that are going to help slow down the positive symptoms of psychosis. And leptic, I mean, we think of sleep, so this is going to help you, like, it's going to help those positive symptoms go to sleep. But then again, the negative symptoms are when you have very flat affect, very, like, you are already asleep. Then we have to mix it up with a atypical antipsychotic. Psychiatric conditions includes neurological conditions. We would have Parkinson's disease included here. And the substantia nigra has a degeneration of dopamine, producing neurons. So actually, it's the lack of dopamine that causes Parkinson's. Because dopamine typically inhibits excessive movement. Which seems a little bit counterintuitive, right? Because you would imagine that dopamine is like activating stuff, right? But no, in this particular case, dopamine is doing the opposite. It is trying to stop you from moving about excessively when your cerebellum is not telling you to do that in the first place. Or, well, it is, but it's not supposed to be, like, you're supposed to be able to control it with the SN. We got the personality disorders. We got different clusters. Yeah, not really sure what else to mention here. Those are the clusters. These are more related to I feel like oddities and eccentricities are a little bit reductive, just because this is more like the cluster that really confuses physicians. Meanwhile, you get a little bit more clear with, yes, this is the more emotional, more dramatic cluster. And there's a bit more of anxiety in cluster C. But I don't tend to think about the clusters too much. That's not really... You wouldn't really consider... Wait a minute. I've never actually seen OCD listed as a personality disorder. Okay. Yeah, OCD itself is completely separate from whatever this is. Oh, okay, interesting. Never actually heard of that. Personality disorder. Okay. So I'm getting the impression that obsessive compulsive personality disorder is more so OCD with persistence, I guess, but it's very unusual of a distinction to make. I haven't really heard that too much before. Well, if we want to talk about anxiety disorders, they're right here. Got your generalized anxiety disorder, but then you got panic attacks in your panic disorder. And you can be afraid of very specific things, and it's a very irrational fear, so you would need really focused exposure therapy to work with that. And social anxiety disorder, more so, is related to being in social situations and having that very intense rejection of social situations because of an extreme, uncontrollable, for the most, well, not for the most part, sorry, uncontrollable without therapy, without focused means of controlling that or managing that, uncontrollable fear for the most part, in that case. Okay. So since we're talking about the medical field, we want to think about somatic symptom disorder just a little bit, just because you're like, if a patient shows up and they think that they have a certain thing and seems like they don't really have that, then we have to start thinking about, well, maybe it's a mental related disorder that we have to parse out for ourselves and see if that's explaining anything. So somatic you have an extreme concern for one symptom, while, you know, illness, anxiety, freaking out about, or sorry, don't want to say freaking out. That is not the right that's not the right way to express what I'm trying to say. It's more so just worry and intense intense worry. That's what I was trying to say. And then the interesting thing is also, another interesting one is factitious disorder. It's when you're making up the illness, but it's not like you're doing that for another purpose. You're not like, oh, hey, I'm sick, so I'm not going to go into work tomorrow. You know, it's not that. You're not doing that so that you can get out of some stuff. You're just doing it. You're just fabricating that for pretty much no reason. And so that is where we consider that to be a mental disorder. All right. Well, there's some psychoactive drugs here, and just want to keep in mind the factors of physical dependence. Had a question show up once that was very insistent that like it had these three options and then one more that sounded very similar to, I think, neurochemical changes, but it was a more dumbed down version of it or something. This is the definition. This is the typical expectation of what physical dependence is, based on what I understood from that question. Well, anyway, got your different types of drugs here. Yeah, not really sure what else to say. These branches kind of speak for themselves, I think. And there you go. All right. Sleep. Well, there's a bunch of different stages, but the cool one is REM cycle. Changes up the dreaming, or it has dreaming occur during that stage. So that's cool. Behavioralism cares about conditioning. And what do I think of when conditioning? Acquisition, extinction, then recovering. And also rewards. When we talk about rewards, we have reinforcements and punishments, which is defined by operant conditioning. So we choose these different types of responses to our trainee. Like if they do something right, we'll give them a reinforcement of some type, or if they do something wrong, then we'll take that, or we'll punish them. And if we take something away from them, that is a negative something. And if we give them something, that is a positive something. And so when we positively reinforce, we're giving them something to motivate them to do it more. And when we negatively reinforce, we take away something bad that they don't want, and that will also incentivize them to do that action, to remove that stimuli. Instinctive drift is when you initially learn something that goes against your natural inclinations. You see this more with like dogs and with animals and such. But then when they learn to go against their instincts, they slowly revert back to going back to those instinctual actions after some time well past the conditioning phase. Taste aversion is a very long-term conditioning where you have tasted something during a bad time in your life for whatever reason, and now you experience some aversion from that taste because you associate that with the very negative situation in which you found yourself in. And then there's different definitions for how these reinforcements tend to happen. Very consistent, inconsistent, it's fixed or variable. And if it's dependent on the ratio or on the responses, then it's the ratio. And if it's on the timing, then it is on the interval. And yeah, there's some certain combinations of these that makes it more resistant to extinction for the needed response. And typically you want some more variability to make it more resistant to extinction. And ideally it's after the ratio, it's with the ratio so that the trainee is learning based on the responses that they have made, as opposed to just realizing that they'll get the thing that they want regardless of if they do the action or not. Or sorry, that's not really how fixed interval works. It's more so they have to do the thing within the time frame, but the fact that the time frame is like pretty linear and consistent makes it so that they are less likely to kind of like care about making the response immediately, if that makes sense. Slow down. Yeah, this is your procrastinating interval. Okay. So there's some study types, and in studies, we got some effects that are messing with, well, that are kind of like changing the subject's ability to respond in a generalizable way to the study, because they'll keep in mind that they are being observed, so Hawthorne effect, and they want to be desirable socially, so they will answer surveys in a more favorable method. That doesn't mean that that doesn't mean that why am I blanking on this? Self-response surveys, basically. Like, if they choose the responses on the survey, that doesn't mean that those won't be reliable, but they may not be perfect in terms of their accuracy. May not be as good as an accuracy point, but pretty reliable. So in that we can figure out some meaning from self-response. All right, and teacher expectancy is a very similar thing to Hawthorne effect. There's the emotional processes, and then James Lang is kind of the simplest version of the non-common sense one. And then Schachter-Signer is the more like complicated version where they include the interpretation, the more advanced James Lang. Whereas Cannon Bard is like a bard shooting two cannons at once to two different spots, the subjective and the arousal. Experience. Cognition has a lot of different branches. There's motivation, and persuasion is related to motivation. There's different types of persuasion that researchers utilize to recruit people, including foot in the door and door in the face. Expectancy is when you expect a reward of some value from doing a thing. So you do the thing and you're motivated to do the thing. But if you put in a lot of effort and you don't see the reward, then you get frustration. Drive reduction. You got a biological need for something. You have a drive to reduce it. Reduce the need by being satisfied, by getting the thing that you need. Got some processing types. Top down is when you have the abstract concept inform your experience, whereas bottom up is the sensation being informative. Language formation. Sapir-Whorf is specific to language forming your perception of the world. Like if you grew up with a very individualistic language, you have a tendency to think more individualistically, things of that nature. Wernicke's and Broca's, I remember Broca being the language production area because it's the one that sounds more what's the word for it? It sounds more simplistic, basically. So you're like, oh, there's no calculations. I'm just saying the thing. Whereas Wernicke's, it sounds more complex. The word or the name Wernicke is like, oh, okay, so I'm comprehending something. I'm calculating things. That's just what it sounds like to me. Like Broca, I will be able to say easier than Wernicke. That's just how I remember it. There's different perspectives on how you learn languages in particular. And you might expect that you would learn it through a critical period in your life. But through practice, you could probably learn it at any time. So interactionists say that, well, it's both. You can do both. And you probably have an easier time earlier in your life learning languages. But later, it's still possible. You can get your attention divided, and it's a little bit easier to divide your attention if they're very similar tasks with low difficulty and with a lot of practice. Elaboration likelihood, I would like to search up right now, actually, because this is the one that I see quite a lot for some reason, and it's difficult to remember exactly what it's trying to point out. It seeks to explore how humans process stimuli differently. So it's kind of the feedback model of learning, essentially, right? Because when you process, let's see. Yeah, when you process a message, there are different ways to like interpret to internalize what you are hearing. I guess this is referring to low, central, and peripheral, I think. In this case, this would actually be over here with central and peripheral processing. If I understand this correctly. Central being like you're utilizing your logic, and peripheral you're just kind of like absorbing because of other factors that you would find more convincing of the likelihood of it being true. And that might be like a famous actor or something saying that this is a thing that is true, and therefore you're like, okay, my peripheral route is telling me, hey, he's right, he's pretty cool. I don't know, I would listen to anything Ryan Gosling says. I mean, that's just how it is. Like, that's the peripheral route. Yeah, all right, cool. Okay, sweet. Self-serving is fun, but I'm wondering if I can find a way to explain how that's different from self-verification. Well. It all loops back around to r/MCAT. Yes, self-serving is attributional. That's what it was. Okay. So it's actually kind of similar to fundamental attribution error. And I think we have that down here. Yes. Oh, interesting. Okay. Right. Anyway. Not to be confused with self-verification, which is just you'll be listening to anything that verifies your point. Verifies what you believe. Functional fictionist is when you restrict your understanding of thing to traditional means. So if you're using a hammer, you won't think about it being possibly used as like a wedge of some kind to break open like a chest or something. You'd imagine that you would hit the chest, like a treasure chest, with the hammer or something like that. And you could do both. Memory. Different types of learning that you can have through non-associative learning, but typically you would see associative learning. And here is your kind of like string of memory types that lead into one another. These are special kinds of memory types that can lead to certain errors. You got that sketch pad, that loop, to form those longer term memories, to kind of like, you utilize your working memory basically to kind of like form those longer term memories through this kind of processing. And these long-term memories form into these distinct types. And episodic, just remember that's more of your personal experience of things, as opposed to semantic is just like straightforward, this is what it is. And you can prime your semantic memory and yeah, make it a little bit easier to encode things. Okay. And speaking of encoding, you got some encoding strategies, which is not the same as associative learning, because you're actually actively encoding things, whereas associating is just kind of more of a passive action or process. And here's some forms of retrieval. Hindsight bias is when you think that you accurately predicted something even though you don't have any proof of that being the case. And here's different types of amnesia and interference. For these ones, remember that retro, like that prefix, is referring to the thing that is getting interrupted. So all of your retro memory, your old memory, is the stuff that's getting interrupted by the interference and by the amnesia. So all of that gets blocked, whereas antero and pro are referring to new memory being disrupted in some way. Korsakoff is a very specific syndrome for a particular type of memory loss that you just have kind of this fabricated set of memories that you didn't choose to lie about, you just kind of had them form. And that can be caused by a vitamin B deficiency. Elderly memory, you have a decline in episodic and fluid intelligence. That's kind of the most basic and most important part to remember, because you'll immediately remember that the rest is going to be pretty stable. Dev Psych, yay, okay. Oh, and I guess hierarchy of needs is included here. Identity development is basically different levels of commitment and exploration to your identity. And when your identity feels like it's already dead, you're not gonna... Or, sorry. If your identity feels like it's already foreclosed, it's already set, you're gonna say that I'm committed to my identity being this way, I'm not gonna explore anything more. Whereas your identity being in a moratorium is more like, yeah, I don't think I'll bother to really commit to any one particular identity. I'm just going to keep on exploring and see what I got. And then these two are on the opposite ends of that spectrum. Where if you achieve identity, you have already explored a lot and you have committed to something that feels most authentic to you. Okay, so we got the different stages, and Piaget, just remember, is the construction stage where you're building up your understanding of the world. At first it's quite simple, and then you begin to understand symbols, understand that you're not the only person here, which is kind of related to the social self stage. Social self stages until you can finally figure out, I have these abstract concepts that make sense and logically fit together. So that's formal. Moral development. And I mean, we can dive really deep into these, but I'm not going to do that here. I just have some mnemonics at the bottom. Ode plug is just how I remember Freud's stages. I don't really remember Erikson's conflict that well with this. I do remember it with this, which is the very crude mnemonic. And I'm a big fan of Resident Evil, so I always think Ada Wong with this. But can she write in crisis, I believe, is referring to like the conflict itself. So there's a lot of progression of mnemonics here, trying to see if I can remember the different stages. specifics on the operation, specifics, construction. All right. PCP, primary care, physician. Nope. That is actually moral development. And I will imitate. So I'm going to, the I is forming from imitation, but the me, the understanding of me as myself and not you, is from playing in games with other people. Different types of therapy, humanistic therapy. If you watched my playthrough of Eliza, this is what that type of therapy is based upon. Very person-centric, trying to figure out your personal problems, trying to work through those. Whereas cognitive behavioral therapy, you're trying to change those negative thoughts and shift them to make them more to empower you, essentially. Psychoanalytical theory got a bunch of different mechanisms to defend yourself from bad thoughts. Here they are. Here's some easier way to remember them. My anime fans out there, reaction formation, those are tsunderes. Or at least those mechanisms are what tsunderes use. It's fantastic. Problem solving. Here's some barriers to that. And we utilize heuristics specifically to take shortcuts. And here's some famous ones. Representativeness is reminding you that you have a mental prototype, but that does not mean that it is representative of real people. That's why we got waifus versus real people right here. Meanwhile, sharks are an example of availability because there's not actually that many shark attacks, but you remember them because they stick in your mind better. They're more theoretically scary. So here's different types of identity, and there's some roles that you have for the self that are interacted in different ways and are present with some conflict between roles and the straining of a singular role, while some roles can exit. Locus of control is how much control you feel like you have in the world, and who is controlling it. If you control it, it's internal. If someone else does, it's external. And if you feel like you're not very confident in something, and that's probably because of something external to you, you're just helpless. You just kind of give up. And that's what learned helplessness is. Dramaturgical is when we kind of consider ourselves to be actors, whether we're on the stage or in the back of the stage. We have different selves. Here's your iceberg for Freud. You have the more consciousness related to the reality principle and perfection principles of ego and superego. Your superego is trying to basically superego is like the glue that keeps the ego and id from separating. So another example from Devil May Cry, Virgil could split his personality into his very logical self or his desire for power, but Virgil himself, the overall character, is defined by his superego being able to merge those two together into one individual. And here's social influence. Normative influence is trying to fit in, but you actually you might want informational. You might want some information, so you'll be influenced by a person that is very knowledgeable about a certain subject. Unlike me. I'm just working through the stuff that I tried to put together. Oh yeah, social support. So if you've watched or read Chainsaw Man, here's kind of an easier way to remember the different types of social support. Emotional, you got Raise, or it could be Makima. But Esteem, well, Pochita is very encouraging. Aki provides tangible resources so that Denji can survive and thrive. Kishibe is providing information and advice to Denji so that he can do better and protect himself. So very informational, very mentor-esque. And Power is just a really great companion. And just really helps Denji kind of like keep himself together as he faces really dire situations. All right, so let's talk about groups. Got different types of group membership, and here we see normative making a comeback. You want to fit in? Well, you should share the goals and values of my membership, right? So that's normative. Utilitarian, you just want the compensation. I'm here for the money. Coercive, you don't have a choice. You have to join me. You have to join this membership or else. And so that's what the different membership types are. Bystander effect, you know, if you see someone in need of help, you might assume that other people around them are going to be more likely to help them. But then when you actually look and wait and see what happens, you'll discover that the other people around that person that needs help, they're not doing anything because they think that you're going to do something. So it's a bad time altogether. Yeah. And I have definitely seen, I've been in a couple situations personally where I saw that, yeah, the bystander effect is a powerful thing. It really messes with you and how you perceive whether or not a person actually needs help. Man, can really screw up some things. But I'm not going to talk about that right now. For now, let's talk about social facilitation. Hey, wait a minute. This is for my performers out there. If you do better in the presence of others, they're socially facilitating you. If you don't, then, well, maybe we'll find yourself in the social anxiety section of our map over there. There's different types of groups. And outgroup, you interact with outgroups, you get some cultural diffusion. That's just how it happens. It's pretty cool. Ideally, more and more people would go out and meet some outgroups that will teach them something new about the world, how other cultures see things, but yeah. Hopefully we can see more of that in the world. It would be a much better place, I think. Unless, well, actually, yeah. However, that can be hindered by groupthink within an in-group, because you get polarized, you get closed-minded. You want to just stick with the in-group, when in actuality it's not good for anyone to be so closed from other outgroups, or from other groups. Here's another Chainsaw Man reference. If you're reading part 2 of Chainsaw Man, you'll understand what this means, what these characters represent. But if not, you know, I think it's pretty straightforward. There's very specific avenues in which case you socialize. And there's different types of kinship in different degrees. Group size is a factor, definitely. Okay. Sociology, finally. We're in the final stretch. So, I'll be right back again. Give me 1 second. Okay, sociology. Functionalism. Got that organism. That societal organism. Conflict. You struggle. You fight for the resources. And you don't work together. Social constructionism. You create constructs within a social framework. Symbolic interactionism is about meaning attached to symbols and things that represent something else. Rational choice is kind of the game theory one. And feminism examines gender inequality. Ethnocentrism is focused on examining ethnic backgrounds and how we collect data based on demographics. Meanwhile, cultural relativism recognizes that cultures are very different from one another, and so if you switch from culture to culture, you get some culture shock. But that all cultures are valid in their differences, essentially. Sociology has some different types of factors that describe society. And on the individual level, you might have capital of certain types, either economic, like the actual tender, the legal tender in which you represent currency, that's economic. And you might have social capital based on your social network, how connected you are, your power through that. And cultural capital, how much you mean to the overall culture. Different types of power. If you're a big Code Geass fan like me, you might see that different types of authority kind of lines up with the three kind of ideological styles, more like, that you see in the series. And these are the three that I came up with, but you could come up with some other ones. Suzaku kind of has to be the rational legal, just because he is so in love with the idea of fixing the world through legal means, but he does take things quite drastically in that approach. And these two are opposed to one another. Charisma trying to overcome the traditional power. Aging is also a thing on a microsociological standpoint. Life course approach is just kind of like, you know, it's considering your aging throughout your life. That's basically it. And this is what happens when you become older and older, and you maintain habits that you did during your youth, so you want to make sure you build those good habits early because of continuity. You see different types of reasons for obedience. And some of these personal factors are related to a person's status, which can be explained by, well, ascribed, achieved, and mastered statuses. Ascribed is you were ascribed by other people to be this thing, so that's kind of what race is all about. Well, by other people, by society, or by other factors. However, if you are able to achieve the status of doctor, in our case, by doing a great MCAT and some other things, then that's an achieved status. And the master status is kind of like, which one of these different statuses are the number one, the one that's dominant in any kind of social interaction, or on the average social interaction. And unfortunately for our ex-convicts in our society, that can be an example of one such master status that kind of is the first to kind of be judged, basically. And whether that's fair is completely up to you to determine based on the factors involved. So you have some types of mobility. This is kind of like along the same plane of existence along with the rest of your generation, intergeneration. But inter is when you talk about how your parents kind of have pushed a certain social status onto you, and how that kind of forms this snowball effect into different generations. And that these statuses can be stratified. Okay. So now we get to macro. This is more society driven. And here's your social classes, which we were talking about here too. Different norms are at play. And here we have some distinctions to describe them. Mores is when you get into the morality aspect of things. And taboos are like the most serious version of mores. While folkways are just kind of like... An example is a VTuber that I watch eats with like scissors or something, right? And so it's like, technically speaking, that's not morally wrong to do, but it's kind of like, it's reckless and is shunned because it's dangerous. That's kind of what folkways is kind of like about. But not morally wrong. Not much relevance to morality. When you are ill, you are expected to do certain things. You have obligations, but you have certain rights to skip work and not be expected to do too much, but with the expectation that you are trying to actually get better. Racialization is when a dominant group kind of like labels a subordinate group. I think this could be also explained through majority and minority relations. And you get certain labels placed on the minority or subordinate group in a societal system that allows such disparity to occur. Unfair labels, by the way, but it is what it is. In the meantime, we have the overall structural factors a society is kind of built on, which is related to its overall ability to space out the wealth amongst different groups of people. So spatial inequality is included with poverty and how we consider those distributions of wealth. It's also concerned with systems between nations. You got the core and the periphery ones. Here's some shout outs to manifest and latent functions. Hidden curricula are part of latent functions. And finally, we get to populations. And here they are. You got expanding, stationary, contraction. Remember that that is a triangle or an upside down parabola or kind of this tapered parabola shape, which kind of looks like a plug. I'm just saying. Again, the crude things that help you remember it, that's you're contracting. You're not like, hey man, whatever helps. There you go. And there's a model that describes where you go from pre-industrial to developed. And yeah, you can expect a population size to decline because people are less concerned with survival and more concerned with self-achievement, essentially. And the Malthusian population growth is related, like it's worried about population growth in relation to sudden crises, and a positive check is kind of a crisis that creates a high death rate, and catastrophes are the biggest version of that. Okay, so I think what was supposed to be a chill review has not been super chill all throughout, and I apologize for that. I feel like Psych-Soc at least was pretty straightforward, but the rest of it, unfortunately, I'm sorry if I was kind of stumbling over some concepts, because the relationships between them are evident in the technicalities of like the equations, but are not always intuitively evident to me when I kind of like tried to describe them. So I apologize for that. I really hope I didn't scare anyone a day before the exam. It's probably me, not you. I hope I didn't burn myself out. I feel like I remember a lot of this information. I just struggled to really like properly connect things as I just described. And I really would have appreciated a bit more time to study, but it is what it is. I'll be taking the test tomorrow, and hey, if I don't do that well, then you can always take it again. You know? Third time might be the charm. But I won't think about that too much. I've been told by a lot of different people, just gotta stay positive. And I think that regardless of what happens tomorrow, the only thing that I really truly hope is actually that I have accurately represented myself on the exam. And yeah. The last thing I just want to leave you with. Yeah, the last thing I want to just leave you with is that this is actually just, this MCAT, just such a small part of something larger. Something more important that I want to just leave off for today. And that is that whatever the MCAT is, it's a small part of what the rest of what life has to offer. Thank you, Aban. I appreciate the kind words, and I really hope that we'll do the best we can tomorrow. Yeah. And thank you all for joining me on this stream. I've already said everything I have to say when it comes to how I feel about the exam and how I feel about my knowledge personally. Definitely could improve the map, but what happens tomorrow happens, and it's just one step towards the rest of what we're going to be working towards throughout our lives, whether that's trying to become a particular kind of physician, or if we discover along the way that like there's different avenues in life that we can explore, then there's that for us too. So, you know, yeah, that's all I want to leave you guys with. So thanks for watching, and good luck to all that are taking it tomorrow and in the future. I imagine that we might have some people checking out the VOD, and treat yourself well, regardless of, well, treat yourself after that test is all I want to say. All right. Thanks for watching. See you later.